Welcome everyone to the image matching workshop, Local Features and Beyond. This is actually the 5th edition we're holding, and I'm Kwang Lee, one of the organizers. I'm speaking on behalf of everyone here. And I would like to, before I begin, give a special shout out to Edward, who's our effective lead organizer, who couldn't be here, unfortunately. But his effort on organizing all of this was immense, and I just wanted that to be credited. And also thanks to Google and Hyper for their generous sponsorship on getting our challenge working as well. We'll talk about that later. So in this workshop, we'll start with the 2 invited talks from Eric and Matthias. We'll be then continuing with having a short coffee break and then continuing with the paper talks and the challenge results. And we'll close by around 12:30 if everything goes well, but we all know that there's going to be a little bit of delays here and there. Hopefully we can make it in time. Also, I want to give a brief mentioning about the poster session that's happening simultaneously, and that's on West Exhibit Hall 185, 194. There are also I think one paper that's presented only as a poster session, so do please go and check it out during the coffee break and other times that you can actually go there. So this challenge, as I mentioned, is the workshop is the 5th edition, which was held every year at CVPR since 2019. I think that's a bit of an achievement that we have, given that we have accepted 26 papers, 9 invited speakers, and also along with all the 5 editions, we also had 5 open challenges, which I'll show briefly later, really a lot of participants worldwide. And as a result of the challenge, we had an IJCV paper as well. And also, if you're interested in previous editions, you can also have a look at online with COVID live streams that are still available. We've learned a great deal from this workshop and the challenge, so I suggest that you also check it out. And to give you a bit of a background for those of you who are here for the first time, this workshop is about local features and beyond, as the title suggests. We're focusing on rigid matching and stereo SFM, cross baselines, time, weather, and whatever changes in the scene that you might see. The common linkage between all of this was, I'm saying was because by the time that the challenge workshop started, the state of the art was local features, and we were investigating actually which local features are best. And of course, we added the beyond because we were foreseeing that local features are not going to stay the state of the art. Actually, perhaps later on, because it seems like they're still somewhat the state of the art. So in 2019, we had this slide, and I think Edward loved this slide so much that we have shown this slide for 5 years in a row. Basically, this is the visualization of us trying to see what's going on, because in 2019, everything else we've been looking into was deep learningified, except for image matching, which was still being done with traditional means. And it's somewhat like the old man yelling at the cloud saying that, hey, we're still using this. We're still sticking to these pipelines that we hold dearly to. And 2023, it turns out 2D to 3D, or matching things and recovering the camera pose and trying to reconstruct scenes, became quite popular. And yes, we know that this number 1 fad and 246 papers includes nerve. But still, it is arguable that it's a very hot topic right now. But the truth of the matter is that even in 2023, there isn't really a better way to large-scale mapping and relocalization than using 3D points and SFM and local features. So seen on the right is the Google Live view that Google provides, which is using Street View images and converting them into trillions of 3D points. And of course, 3D points means local features. And one of the things that we've noticed that motivated our workshop is that when it comes to large-scale SFM deployments, people still rely on CoalMap and SIFT. And this is somewhat surprising if you think about the fact that SIFT performance has been beaten, at least in literature, since, let's say, 2014 here, according to this slide. So there is a large gap comparing SIFT performances with other later on developed local features that are learned as well. And yet still people rely on CoalMap. So this was one of the main motivations that we created this workshop. So the short answer to the phenomenon that SIFT and CoalMap is still the de facto standard is because SIFT is not bad. And according to benchmarks that I've shown until 2019, it didn't really show that. Like, it really showed that SIFT is really bad and you should replace it with other things. But in the downstream actual industry or SFM performances, that wasn't really the case. And in fact, even in 2023, some of these benchmarks, such as H-patches, that's a little bit focusing more on the planar structures, are still being used as sometimes even the only benchmark out there. And that doesn't capture the entire view of how things work. So our proposal was an open challenge, and it was ran every year since 2019. And we created a benchmark suite and a set of data sets that you can actually run. And then that resulted in a JCB paper that somewhat shows what's more close to the things that you can expect when you use these local features for 3D reconstruction. And we were evaluating based on downstream performances, such as camera poses, which is effectively what you would want at the end if you're interested in reconstruction. There are other ways of doing this now. Of course, we're not the only people thinking about this problem. There's visuallocalization.net, which evaluates also using the downstream performance, in this case, using localization. So the first 3 years of our challenge was an academic challenge. We hosted in academic servers and in-house solutions. We ran it on our own clusters, and a poor graduate student was assigned to run all the submissions that was given. And it was still, I think, a success, given that on an academic setup, handling about 100 submissions was already challenging. And there were around 28, 25 teams. And then 2022, somebody, Edward actually spent a lot of time migrating to Kaggle, and a lot of core paperwork had to be done. But I think it was worth it given the number of teams increased by 20 to 25 times and number of submissions 150-fold. So yeah, so there are red bars there. Tiny, big, tiny, teeny, but there are red bars there showing the relative number of participants and scale that we were able to achieve. So moving to Kaggle did attract a lot of interest from many Kagglers. And in 2023, from 2022, the main thing that changed was to move to Kaggle, we had to rely on stereo task, meaning that you were supposed to match us 2 images. Now, in 2023, we moved that to actual SFM reconstruction and using CoalMap or whatever reconstruction method of your choice to do pose estimation and evaluate in an SFM setup. It's a much more difficult setup, as you will see later. And so in summary, we moved to stereo to SFM from stereo. And also, we introduced some new data sets that were distinct and has their own characteristics when it comes to the focus that these data set subsets are focusing on. And one of the reasons that we did that is because we wanted to address the issue that we had from last year, trying to get training and testing data, so the public and the hidden split to be really large. And finally, yes, we did have a substantial increase in the prize pool, $50K US, again, thanks to the sponsors, Google, Hyper, and Kaggle. So let me give you a
cover later. We are kind of already at time.
Okay, I'm getting kicked out. So, yes, so about the data sets, I will talk about it later. And since we're on time, I will then move to a few slides later. Let's go to, not the coffee break just yet, to the invited talks from our speakers. So the first speaker that we have is Eric Brahman. I'm always scared of pronouncing last names because, to be fair, I have also a last name that's always been long. So, Eric is a staff scientist at Niantic, working on ship visual positioning systems. And he works at the intersection of machine learning and computer vision, 3D vision in particular. His research involves around topics as localization, pose estimation, and robust optimizing feature learning. My favorite work from Eric is actually his line of research on differentiable ransack and learnable ransack, which is quite amazing. So I'll stop speaking and hand the stage over to Eric. Once the screen share is properly done.
Okay, one moment.
Continue speaking on this.
Yes. I'll continue speaking while Eric allows his laptop to share his screen.
Yeah, it's a new laptop, of course.
Yeah, I mean, it's for security's sake, right? So
yes.
Nobody wants anybody spying on your.
Oh no, I have to.
No, not this time. You are.
But I have to leave and rejoin.
Why?
Because I have.
Okay. Wait. Let me reclaim cost. Yeah, now you can leave.
Yeah, we almost accidentally closed the Zoom session. So. Good call.
Okay, should I make you again? Okay. Yes.
There you go. You might want to also enable optimization for videos if you have videos.
I have.
Yes, it's on the top of your screen.
Yes.
Stop share and then reshare.
So where did I
click share? And yeah, just click share.
Yeah.
And then here
optimize the video.
Ah.
So
what? Like, share your audio.
No, you don't share audio unless you want to share audio. That's fine. You're good. You're good. You can.
I take it.
Yes. And,
but this is now optimized for video.
Yes.
Should be.
Yeah. Okay. Hello, everyone. I'm Eric. It's a pleasure to give this talk on pose estimation beyond feature matching. I was already introduced, but here's some contact information about myself. But the people who are actually here in Vancouver, they of course can also meet me here. I'm a staff scientist at Niantic. And to motivate the talk, I want to retell a story that has been told many times. And in fact, it has just been retold in the intro of this this session. So 10 years ago or so, we only had SIFT and there was no real alternative. And then there came deep learning and researchers were like, okay, I want that. And there were early successes in learning features. People went to H patches and reported great results on these benchmarks. Like here we see a comparison of SIFT and Superpoint, and Superpoint does a good job. This was before Superpoint. But then people actually tried to use it for something, and suddenly the improvement just went away. So here we see relative pose estimation results, and suddenly RootSIFT was doing a better job than Superpoint again. This is just to say, if you work on local features, it's a good idea to do it for a specific task. And this is what actually happens. The IMC challenge, it now evaluates using pose estimation and SFM, and that's a good idea. That's basically what this slide says. And one of the tasks that you can use local features for is visual relocalization. Visual relocalization consists of two steps. You have a mapping stage and you have a relocalization stage. In the mapping stage, you take images of a scene and you build a 3D reconstruction of that scene. And if you want to use local features for that, you obtain poses for the mapping images, for example, using visual odometry or SLAM or SFM. And depending on how you obtain the poses, then you triangulate the scene. And for highest accuracy, you bundle adjust everything. And then comes the relocalization stage where you want to register new query images to the scene. And if you want to use local features, then you do it via discrete matching. You can use image retrieval to reduce your search space. You do discrete feature matching, and then you optimize poses using RANSAC and PNP. So is this a useful task? I would say yes. I work for Niantic. Niantic has a tech stack open for developers. One part of this tech stack is a visual positioning system, which at the moment works at 200,000 locations worldwide, also in Vancouver, and it allows for augmented reality experiences like this one. This talk is called, feature matching and beyond. The visual positioning system of Niantic uses feature matching as one component, but it also uses something different, a learning-based approach as an alternative. And the learning-based approach to this date is responsible for most relocalizations. So there is something else out there which works very well. But let's first, as a baseline for this talk, discuss a feature matching solution to relocalization. And this is in particular the relocalization stage that I'm talking about here. So you have a query image that you want to relocalize, and you have a 3D map that you have built in the mapping stage, for example, using SFM. And now we go through the pipeline. So you might use image retrieval to get the mapping images that are relevant for your query image. Then you extract your feature points. There is some slight delay here. Then you match these features. And because you have triangulated the scene, you can look up the 3D coordinates of the points in the mapping image, which induces a 2D 3D correspondences. So you can solve for the pose with RANSAC and PNP in line accounting. And this gives you the final pose. Great. So this is a feature-based solution to relocalization. And it works very well. It's very accurate, but there are also downsides. One downside is the query time is moderate. Depending on how you do it, discrete feature matching can be expensive. If you have lots of features, if you have a large point cloud, and you have high dimensional features, it can take some time. The mapping time can be slow. If you run SFM and you have to bundle adjust everything, that can take a long time if you have many mapping images. And if you have to store a large point cloud with high dimensional features, that can cost a lot of memory for storing these maps. So, okay, there are some downsides. Like, let's look at alternatives. What else can you do? So you could say, well, I throw all the steps out of the window and just train a neural network to do everything. It takes an image and it produces a pose. You can train such a network with your mapping data. You have mapping images and poses, ground truth poses, and you just train a network. And your network somehow learns an implicit hidden representation of the scene. in which you try to relocalize. Let's look at results. How well does this do? So here's the diagram. On the y-axis, there is the median positioning error. So how good are these systems? And on the x-axis is time. When were these methods published? And this is on a large, on a small scale indoor data set. And to establish some context, some boundaries, feature matching on this data set allows you to get to centimeter accuracy. And as a somewhat baseline, you can also use image retrieval to just get the closest mapping pose and use that as a proxy for your query pose. And this would get you on this data set to 26 centimeters of accuracy. So how is absolute pose regression doing? So this is the graph of these methods. And there are two ways to read this graph. There's an optimistic reading, which says, well, you know, there's progress. It clearly goes down. And at some point, these methods will overtake feature matching and yield high accuracy. And there's the pessimistic reading, which says, well, you know, we have worked on this for 10 years, almost 10 years, and we still are not able to beat feature matching. And this feature matching here is SIFT. Okay, so conclusion for absolute pose regression, they are fast at query time because it's just a forward pass to get you to the pose. They are slow at mapping time because you have to train a network for each scene. Memory demand is moderate because these networks tend to be large, and the accuracy is also moderate. We have seen progress, but still it's not there yet. Okay, what else can we do? There is a method which is called correspondence regression or scene coordinate regression. It's very similar to feature matching, but it merges the steps of feature extraction and matching into one step, correspondence regression. And it works like this. So you have your 3D scene, and you have the query image that you want to relocalize. And you say, all the points in your scene, all the surface points, have a coordinate in the reference frame of that scene. And we can visualize these coordinates by mapping X, Y, Z to the RGB cube. And now you train a network which predicts these scene coordinates for all the pixels of the input image. So this prediction induces a dense 2D 3D correspondence field. For each pixel, you get this 3D coordinate of the scene. And this allows you to use RANSAC and PNP to register your query image and get the pose. You train these networks using, by optimizing reprojection error over your mapping data. And this took a long time until recently, but at the CVPR, we have a paper where we show that you can actually train these networks in minutes. Here I show a training run in seconds. So this is real-time training of these such a system. And then you relocalize with very high accuracy. So if you're interested in this, you can visit us at our poster tomorrow. Right, so this is an alternative, correspondence regression. Fast query time because you get the correspondences immediately with a forward pass. You don't have to do discrete matching. Mapping time was awful. Now it's moderate, I would say. You still have to spend a few minutes on a GPU. It's okay, but it's not ideal. Memory demand is low. These networks are relatively small. Accuracy is high, definitely competitive with feature matching. Right, but what else? So the last alternative I want to talk about today is relative pose regression. It's almost like absolute pose regression, but it builds on image retrieval. So we have these 3 stages again, or 2 stages, and there's an extra stage preparation. So you do some pre-training. You pre-train image retrieval. So you have a method that takes a large image corpus, all your mapping images, and can extract for your query image relevant mapping image. This is something you need, and you need to pre-train, but you only have to do it once. Doesn't matter how long this takes. And then you pre-train a scene agnostic, a generic relative pose regressor, which just takes 2 images of the same scene and tells you the relative pose between them. Then at mapping time, you don't have to train anything. You just take your mapping images, you obtain poses, visual odometry, for example, you build a retrieval index, and that's it. And that's very fast because you don't have to build a reconstruction. You don't have to train. And at relocalization time, you have a query image. You look up the nearest neighbor mapping image, and then you apply your generalistic relative pose regressor to tell you the relative pose between these two images. There is a problem though, as many of you skilled people here probably know, from two images, we cannot infer the scale of the translation, the distance between the cameras. If this bear here was a toy bear, then the distance of the two cameras would probably be a few centimeters. If it is life-sized, then it is probably 1 or 2 meters, the distance. And via geometric reasoning, you cannot really tell. But you could say, well, there are heuristic ways to infer the scale, the approximate scale of this. So a network could tell maybe, it's probably life size, there's a bench in the background and so on. And you can guess the scale of things, but it will always rely on heuristics. It will always be somewhat approximate. And this is what we also see in experiments. If you train a relative pose regressor on the exact scene you want to relocalize, you get higher accuracy than using a generic relative pose regressor. And there is an alternative. There is a geometric solution to this, which involves relying on more than one mapping image. So you have your query image, you get the nearest neighbor mapping pose, and you get an estimate of the translation vector up to scale. And you do this for more than one mapping image, which gives you more than one estimate of the translation direction. And this allows you to triangulate the position of the camera pose. And this is the geometric solution, which doesn't rely on heuristics. Here we see a comparison of these methods. Not yet, but now. This is the same data set again. We have 2 single-shot relative pose regression methods with circles and 3 methods which rely on pose triangulation. And they perform better on this data set. And the best ones are feature matching based. So you can apply superglue and lofter to get essential metrics, decompose it, and then triangulate the pose. And this is the best relative pose regression approach that you can use. So conclusion for that part, things tend to be fast at mapping time, because even if you use matching, you only have to use matching for pair of images. Mapping time is fast because you don't have to reconstruct anything. Memory demand tends to be low. It depends. If you use feature matching, then you have to store the mapping images. Then it can be expensive to store all these images. If you use relative pose regression, then some of these can work on global image descriptors, which are cheaper to store. But in any case, the accuracy is only moderate. How am I doing on time?
Okay.
How much?
You spent 15 minutes.
Okay, because this is not the conclusion of the talk. The slide is full with all the approaches, but it's not done yet. Because I want to return to this plot. We thought, okay, maybe this data set is too friendly for for this triangulation approaches. Because in this data set, someone really spent a lot of time to scan these indoor scenes. Someone went there, scanned it multiple times. We have multiple thousand mapping images for these tiny little scenes here. And we thought, maybe that's too friendly for triangulation. You always will get, with image retrieval, multiple relevant mapping images for your query image. And then, of course, you can triangulate. What if we don't have that much? So we did an experiment. We subsampled the mapping images and just used 10 frames to represent a scene. And what we see is, hooray, our relative pose regression network, or single-shot relative pose regressor, beats SIFT. We beat the feature matching solution. Wow, we are so amazing. But of course, we know that today, SIFT is not the best thing you can do, so you have better methods now, and we lose heart to these. These are still much better, but we are not done yet. Okay, what if we use 5 frames to represent each room? Didn't really change. Let's go on. 2 frames to represent each room. Now we did it. We beat superglue, we beat lofter, and we beat SIFT. But we are not done yet. We can do more. We can represent each room with a single frame. And then the competition is gone. because you cannot triangulate anymore poses. Relative pose regression is the only thing we can do. We have done it beyond feature matching. We've beaten everything, but it's not really true because you can do something else. So we know with feature matching, we get relative pose up to scale via geometric reasoning, essential matrix decomposition. And then we can use a depth estimation network to give us the scale of the translation. So there are networks which predict the absolute depth of scenes. They are pre-trained on some data and can estimate absolute depth. And if you combine the two, then you get a scaled estimate of the pose relative to a single image. And if you do that, much better than relative pose regression. So feature matching is back in the game. Okay. But there is something in this plot which is easy to miss. Something that happened when you go from 1,000 frames to 10 frames to 5 frames to 2 frames to 1 frame. And the step from 2 frames to 1 frame is actually crucial, because with 1,000 frames, you need to have poses, all of these. With 10 frames, you still need that. With 5 frames, you need that. With 2 frames, you still need that. And arguably, it's now more difficult, because if you represent a room with 2 frames, and you have to estimate ground truth pose between them, between the reference views, maybe there's no overlap anymore, or there's hardly any overlap. So how do you do that? SFM will probably not work. Visual odometry, you need continuous tracking between the 2 frames to get the relative pose. But if you only use 1 frame, you don't need poses anymore, because the single frame gets the identity pose. So the mapping stage actually, in a sense, degenerates to just taking the picture. You don't need a pose anymore. There's nothing more. The mapping time is 0. And then during relocalization, you just apply your relative pose regression approach, whether it's feature-based or network-based, and then you have the pose of your image. I really want to celebrate this. You should take a single picture, and then you have some kind of learning-based method which defines a metric space based on this single image, which allows you to relocalize new views in the same space. We were so excited about this that we rebranded this instantiation of visual relocalization and this instantiation of relative pose regression and called it, this is map-free relocalization, because you don't have to build a map anymore, not even a retrieval index, nothing. It's all based on a single image. So you might ask, well, okay, you can do that, of course, but does it work? You've seen in the graph, the errors go up, right? Is it still useful to do this? And here's an example from this indoor data set. We have the reference image, we have many query images, and here you see some qualitative results of the relative pose regressor and of supergroup. Each dot is an estimate, and we color it by error, and we use a reprojection error here with a relatively large threshold. But the threshold where you would still say, okay, this can still be useful for some AR applications. And you see some of the dots are green, actually many of them. So yes, this can be useful. But, you know, these indoor rooms are maybe not suitable for this because it's very hard to capture the essence of a room in a single image. But there are places like this outdoors. There are places which are actually quite well captured by a single frame. And it turns out that Niantic's games are built around these places. And we have players taking scans of these places. So this allowed us, you know, to capture a few of these, a few hundred scenes like this, and create a data set for this. So we have a few hundred scenes scanned twice by our users, and we reconstructed them with SFM to register the scans together to get ground truth poses, everything's bundle adjusted. So even if you don't care about map-free relocalization, we have the SFM models for a few hundred scenes, outdoor scenes online, so maybe they are useful for you, even if you don't care about this task. Here's an example of 2 of these scans. So users approach these places differently. We have one user here who scanned up close and did a 360 around the statue. Then we have a second user who scanned from further away and did not a full 360 sweep. We split the data set into training set with 460 scenes, where you have full 2 scans to harvest pairs of frames as you wish. And then we have 65 scenes for validation and 130 scenes for testing. For validation and testing, we have to do one more step. We have to select a reference image for that place. So from one scan, we select a single image, which kind of represents it well. And then the second scan serves as a source for query images. These places were collected worldwide with a focus on North America, Europe, and Japan. And here are some statistics. So 25% of scans were taken on the same day, maybe by the same user. 25% were taken within a week, 25% were taken within a month, and 25% were taken within 6 months. So we have different times of days. We have also season changes. But you know, these are structured mostly urban environments. So here's an example of an actual season change. So you see there is snow in the second scan and the plants have lost their leaves, but it's not so different, you know, even though there's a season change. But you know, it's real data. This is what it looks like. Then we have overlap score. This is an SFM overlap metric, so co-visible SFM points. And we have a nice distribution over different overlaps. And you might notice the spike for 0 overlap. So what's that about? Where, you know, if you select a single reference image and you have query images of people exploring this environment, you will go to the point where there's actually no visual overlap anymore. And we will come back to these cases, what we do about them. In terms of post difference between a reference image and query image in the test set, we see the distribution here of angular difference and translation difference. So if we pick the median point in this plot, you'll see that the median rotation difference of image pairs is 45 degrees roughly. 50% have less rotation difference, 50% have more rotation difference. And the median translation distance is, I think, 3 meters. So here we have an extreme example where the reference image is close up and many of the query images are from further away. So quite a scale change that you have to deal with. Okay, let's look at some qualitative results. Does this work at all? Right, and these are results here of feature matching. So you use superglue and you use depth estimates from a transformer. So let's look at some easy scenes as like motivation to see it's not hopeless. Actually, it's a small place, and you see the estimated camera frustum follows the transverse camera frustum quite closely and traces out a nice trajectory. One more scene where it works well, I think in this case, these 2 scans were taken on the same day because you see the same car parked in the background. And, you know, feature matching can deal with it. It works. And it's a scaled estimate. You know that you can estimate the distance to the object relatively well. One more nice scene where it works. So this is already more difficult, right? Because it's abstract statue, but still the depth estimation network seems to be able to somehow estimate the correct depth and allow us to follow the transit trajectory okay-ish. But that's really it. I cherry-picked these scenes to show you something where it works. Let's go to more difficult examples. So here we have a scene where we actually turn around the object. And as long as you're in the front, it works. But then as you move around and there's self-occlusion, it breaks down. And you can imagine why, because the feature matcher doesn't find correspondences anymore. And it's not a visual overlap problem, right? It's a problem of self-occlusion. The feature matcher could find the corresponding projection of each correspondence if it reasons about fore and background of these objects. But it doesn't. It's low-level matching. So as soon as the viewpoint changes too much, it just breaks down. And then the depth estimate just spirals out of control. And the depth estimate, the pose estimate, spirals out of control. Here's another problem. Here, the feature matching does a decent job. You see that because the orientation of the estimate is okay, but the scale is off. The depth estimation network is not able to estimate correct depth for this particular scene. And we have to say there are not so many scaled depth estimation networks out there. This is DPT, which was fine-tuned on Kitty. This was really the best choice, although it's an awful choice. Okay, let's move to relative pose regression and network now, not feature matching, and network. How does the network deal with this? No, okay, it's the same scene, and we have seen before that the scale was off for feature matching, but here it's not perfect, but it follows the ground truth trajectory, ground truth frustum bocage, I would say. So approximately, heuristically, it's doing a good job. How much time do I have?
15 minutes.
15 minutes, great. Okay, one more difficult scene. So here we start from far away. Again, relative pose regression. We move towards the thing and move around it. And you know, relative pose regression, again, approximately, it's doing a good job. It's not awful, not great either. But if we compare it to feature matching, then you see hope for these methods. Because feature matching, when it works very accurately. If it finds correspondences, then it's mostly spot on. But if the viewpoint change is too big, it just breaks down. Whereas relative pose regression somehow is a very nice approximate solution. The red one is relative pose regression, the yellow one is feature matching. Here we have another example. A well, and the query camera does a 360 turn around the well. And you will see feature matching doesn't really deal with that, so it breaks down. But relative pose regression, I mean, if you're positive about this kind of methods, you see somehow, yeah, that it follows the query frustum around the well. So it somehow reasons about the 3D world and the objectiveness of objects. And that's, I think, it's quite cool. Another example, and this is a rare instance where the relative pose regressor is actually more accurate than feature matching. So it's more, there's less variance in the estimates. On the left, superflu, and it's quite dispersed, the estimates. But for the relative pose regressor, it's quite a nice trajectory. And this, I think, is my favorite example, which is coming now. The front and the back of the sign is identical. There's the same text on it. And you will see it, if you look at the yellow frustum, superflu, it snaps back to the front as you move around the sign, because it's just confusing. It's the same sign, front and back. But somehow the relative pose regressor can distinguish front and back, although the sign is the self. And this, I think, is really exciting and amazing, because you see glimpses of higher level reasoning. It somehow sees, yeah, but the background doesn't check out. Because of the background, it probably can distinguish, oh, I'm on the back of the sign, not on. Okay, so we have seen some qualitative examples, but how do we evaluate this? So I think it's a good idea to define a pose threshold. What is a good pose? What's a bad pose? You could define a threshold on the precision error, for example, but we have different scales of scenes. So one threshold might be too strict for one scene and too loose for another scene. So we decided to go something reprojection based, something which is motivated by augmented reality and the placement of virtual objects. So we say, okay, you could place a virtual object into the scene. You see these boxes here, and we measure where is it projected with the ground truth pose, where is it projected with the estimated pose, and how much is the difference, the perceived error, basically. We don't know where objects would be placed by users, so we just use a grid of possible positions. Then we average the reprojection error over all of these objects. And here you see an instance where the boxes placed by Superflu are decent, right? It's not awful. They are where they're supposed to be, and that would allow for a good augmented reality experience. So in terms of quantitative evaluation, something you could do is a graph like this. On the x-axis, you have the reprojection error threshold, when is a pose good? And on the y-axis, you have the ratio of images solved by a method within this pose threshold. And we have 3 vertical bars corresponding to 1, 5, and 10% of the image diagonal. 10% of the image diagonal is quite big error. You would see that. But I would say on your phone, if you have 10% offset in the diagonal of your phone's resolution, it's not awful. It's not horrible. You will see it, but maybe it's still useful for some augmented reality applications. And here we see the results of Superflu, where for a 10% threshold, it would solve approximately 35% of image pairs. Lofter is almost the same, and SIFT is quite a bit worse. And here we see the results of relative pose regression, and this confirms what we have seen in the qualitative results. For low thresholds, like 1% of the image diagonal, it solves nothing. It's awful. It's not precise enough. But for large thresholds, if you accept coarser estimates, then relative pose regression actually overtakes feature matching here. But there's a problem with this evaluation because it plans out a very important aspect of this kind of task. And this is visual overlap. So as we have discussed before, we have scenes and we have pairs where there is no visual overlap whatsoever between the reference image and the real image. So what do? We could filter out these pairs and say we remove them from the test set. But we don't want to do that for 2 reasons. Reason 1 is we don't want to tell you what you are able to solve. There are creative people out there. Maybe they come up with something which approximately allows to solve low or no visual overlap pairs. The second reason is that in an application, this is important. There might be no overlap between the query image of the user and the reference image. So what does the system do? Just return a random pose? That's awful. It should tell the user it's not able to solve it. There is no estimate possible. So we do an evaluation which is inspired by precision recall curves and object detection. On the y-axis, you have the precision. So how many image pairs are you able to solve? And on the x-axis, you have the ratio of confidence samples. You sort all the estimates according to the confidence of the method. And then you move this confidence threshold throughout this list such that you have 25% of, we all see the chat.
Sorry.
You have 25% of estimates within the threshold, 50%, and so on. Here we see the result of Superflu. Superflu, up to 25% of estimates has a precision around 80% of correctly estimated poses, and then it drops down gracefully. But you see, it's not perfect. Even for the highest confidence estimates, it's not 100% precision. So wrong estimates still slips through. Lofter is doing a slightly better job. So at least for the highest confidence estimates, it's also correct. And in fact, SIFT, for the highest confidence ones, is even more reliable. So if SIFT is very confident, and this is inlier counting, by the way, confidence means you count the inliers that you get. Then you can trust SIFT, but SIFT has a steep fall-off, so then it gets worse than the other methods. What about relative pose regression? These networks don't give you confidence. They just spit out a pose for anything that you get back. And that's a huge problem in this kind of evaluation. Because if there's no confidence, the sorting of estimates is random and this curve will be flat. You just get the average precision of all the estimates. So this is the final evaluation that we propose. And this is the results that you get as an area under the curve, as a metric that you can calculate. And Lofter faintly wins over Superglue because it has a slightly better confidence estimate. The inliers are more reliable. SIFT is quite a bit worse. And relative post-regression, just because it has no confidence, loses heart here. So if you would come up with a solution for the confidence problem, then it might be that relative post-regression jumps to the top of this list. And here we see an example where we use the confidence of Superglue, the inliers, to mask out low confidence examples. So when it's gray, then it's not reliable and we don't use the estimate. But you can see still some wrong estimates slip through. And here we have used an inlier count of 70. So some wrong estimates have still 70 inliers and still are reported back by the system. We have an online leaderboard. The test ground truth is private. So you have to use an evaluation service to get your results, but there's a huge validation set to tune your hyperparameters. We try to make this as accessible as possible. Data set is online. All the baselines are online. You have pre-computed correspondences online. You have pre-computed depth estimates online. So if you just want to work on correspondence estimation, you can use our depth estimates. If you just want to improve the depth estimates, you can reuse our correspondences and so on. There's an evaluation service and a leaderboard. And this is the conclusion to the talk. Thank you so much.
So I guess it's time for questions. While we wait for other questions, I already have a question from the chat. Do you think it is possible to take temporal considerations to improve stability, accuracy of camera positions? How would you suggest incorporate it in the framework if possible?
Yeah, that's a good question. We do not consider it in this benchmark. This benchmark is designed to really push forward the capabilities of two-frame pose estimation. That's our goal, to see how far can we go? How far can we push these heuristic solutions? It will always be heuristic because of the scale ambiguity, but how far can you push it? Because if you allow multiple frames for your queries, and not just one query frame, but multiple, what you can actually do is reconstruct the query sequence and then register the reference image to your query reconstruction, basically inverse relocalization. And that would be relatively easy in terms of pose estimation. You can also do temporal filtering like Kalman filter, which this would use this in practice, of course. If you have a query sequence, then you would use filtering, temporal filtering to get the results more stable. But in terms of this benchmark, we don't want to do that.
I see. So anybody? Yes, sorry.
So a couple of questions.
I think we can line
first
up
one,
there.
if the depth estimate is wrong, then the RPR will also be punished exactly like the feature-based methods. Is it correct that the absolute scale of the estimate is the same because it depends on the same depth estimate?
No, the relative pose regressor doesn't rely on the depth estimate.
So it has some sort of depth inside because it gets, so it sort of has its own depth estimate.
Yeah, it has its own depth estimate. So the network that we use uses a correlation volume in the middle and then regresses the absolute pose from the correlation volume. But the correlation volume also uses warp features. So it has access to the image features, which are piped to the final result, and it has its own estimate of depth. And actually, it has an advantage because the relative pose regression network was trained on this domain of scenes.
Exactly. So that was my second question, that you would fine-tune your depth estimate on your training set, and you would probably get a little bit better.
You could, but there are not so many depth estimation pipelines out there which allow you to just train or refine from pairs of images with poses. Usually they need ground truth depth. So you have to reconstruct it, you have to get ground truth depth for these scenes, which we do not have. So there's a a tail attached to that. But you can do that, yes, you should.
Okay. And the second question
Yeah.
is, what is your precision of your ground truth? Because that might end up being maybe on par with the most accurate estimates from the query. So do you have some knowledge or of that?
No, I don't have, and I love the question because this is something which keeps me up at night as well. So how good is our ground truth? I don't.
You could say how you computed it.
Yeah, it's a core map reconstruction of these scenes. It's bundle adjusted. The scenes are not so far away, so I'm hopeful that the accuracy is okay, and our thresholds, our acceptance thresholds, are quite big. So we hope that the inaccuracies of the ground truth are within limits that are acceptable compared to our large evaluation thresholds.
In terms of the feature matching baselines, what do you think the bottleneck is? Like, for example, is it about the feature matching not being able to estimate the correct correspondences, or is it about the depth estimation systems not being able to actually recover the geometry correctly?
It's both, I think, but I think there is room for improvement on both sides as well. So for the feature matching, it seems to be mostly still low-level matching. So it tries to find the same surface, basically, and make the correspondence. What it should do, and there are methods like this, is hallucinate the corresponding point in 3D. So I have a point in A, where does it project to in B, even if it's not visible, if it's behind something, if it's self-occluded. And I think there are not many such systems now, but I think some works do that, and maybe that's a better approach.
Thank you.
Okay. Hello.
So you show that relative post regression is robust to viewpoint changes, while when feature matching works, it's accurate.
Yes.
Is there any reason against using them together? I mean, relative post regression to use as a coarse estimate, which you use as a guidance for feature matching and also for the depth estimation.
Very good. Yeah, that sounds very interesting. It would also be good to then train them together. And we focus on the task and the benchmark, and there is so much you can do to immediately improve what we have. We just used off-the-shelf stuff. And I can see many approaches to improve things, and this is definitely one.
Let's talk about the next CVPR paper.
Yes, absolutely.
Thanks.
Great presentation. I do have basic question and more advanced question. The basic question: in your baseline, you are using SIFT. So to compare to, I was wondering why didn't you choose like area-based matching as a comparison?
What matching? Sorry?
Area-based matching.
Area-based matching.
And my follow-up question, now we have a lot of satellite imagery, so it's comparable to terrestrial imagery. Based on your experience, how you think this kind of method could be extended to this kind of imagery?
What kind of imagery?
Satellite imagery.
Satellite imagery. I think that's not so. Second question first: the matching of satellite imagery to ground images. That's not my area of expertise. I cannot comment on that. So, yeah, it's very interesting, but I think it's a different task. In terms of our baselines, I think there are many more baselines we could have used. We took the most popular ones, I guess. So Loftus, Superglue, SIFT. We really tried to push what is possible with all of the methods that we looked at, right? But we had to make a choice what to use.
Thank you.
All right. Yes, last question.
Quick question. So about this relative post estimation, does the network have to sort of memorize the scene? So can it scale the same way as feature matching?
It doesn't memorize the scene because it was trained on a distinct set of scenes. So we train the relative post regressor on this domain of scenes. So the training set is similar scenes, but we test it always on unseen scenes. Okay, so it's never trained on these particular scenes. So you can apply it scales as well as feature matching. You can apply it on any new scenes without any retraining.
Oh,
last question.
Sorry.
Yeah.
Is there any sensitivity towards lighting conditions? Have you tested on scenes where you actually have a lot of lighting conditions within?
We have a few of these in the data set, but not that many. Because of how our data pipeline works, somehow there's not that much lighting change in there. But I think also people tend to overestimate lighting changes, maybe based on some academic benchmarks that are out there. In urban environments, they are mostly well lit also at night, and people really they overestimate the difference of day and night.
Yes.
Scenes in urban environments. And if there are more questions, I'm around, right? So you can always ask. Thank you.
Let's give it a shot.
No,
you can keep that.
Like, are you connected to Zoom?
Yeah.
I don't see you.
I'm logged in the wrong account. Just ignore me.
So which one? You?
It's a long story why I have it right now.
Okay.
All right, so we are aware there are some questions in Zoom as well. Yeah, so sorry, you please we'll relay the questions to Eric as well. So
No, it's
hopefully he
CVPR
can
Zoom.
answer it.
You just share the Zoom.
Oh, I see.
Okay, in the meantime, let me introduce Matthias Nisser, who is lead of AI lab at TU Munich. He doesn't really need any introduction. He's, I think, one of the person for nerve mesh and all this kind of reconstruction and multi-view matching. So, it's yours.
Yeah, thanks so much. Okay, I hope you can see it. Is it working on Zoom too? I guess so.
Yeah.
Okay, yeah, so this talk, I'm not going to talk about nerve. I want to talk about multi-view feature matching to make it a bit more appropriate for the workshop. So I wanted to start maybe with a little bit of history, how I actually got into computer vision. And for me, what was really cool when the Kinect came out was that you could actually create 3D models in real time, get a depth map, and it was a device that cost $100. And it was about 2011, 2012, when people started using this in computer vision, and you could all do kinds of tasks with it. Because originally I came from computer graphics, and I wanted to use these 3D models for content creation scenarios, right? And I think still the Kinect is still a very remarkable device, and I think it speaks for itself that many research papers, even today, use that kind of data, and we have many data sets built around it. I think Eric showed a bunch of examples from the Microsoft data set where they had this chess examples and so on for the scene coordinate forests. I think this was 7 scenes data set, right? And there's still many around it, and it's kind of remarkable. And I was really amazed by that. And I was really curious of getting reconstructions to work that are very robust, but also can take very large scenes into account. And one of the first works that I was involved in was this voxel hashing work. And it was in a similar spirit to Kinect Vision, where you take an input R2PD stream, and in real time, you wanted to create a 3D model, and the 3D model was stored as a sign distance field, and it was integrating the sign distance values based on the depth maps that you're getting all the time. And the core idea behind that method was that, well, many of the methods at the time were using these sign distance fields. Sign distance fields is an implicit scene representation that was originally introduced by Curls and Levoy for 3D reconstruction. And these guys are storing basically a dense grid of voxels where each voxel stores a sign distance value and a weight. And so the more weight, the more depth values you're getting right now, you're just updating this with the running average. And then at the end of the day, once you're done with your scanning, you can run on margin cubes and get your mesh out of it. But the problem is this grows cubically, right? So what we did at the time, we thought, well, can we do this with the better scene data structure? And in computer graphics, people actually used a lot of these data structures for spatial partitioning. And what we did is we used spatial hashes. And this is a really straightforward idea that is still used today in quite a lot of applications. So the idea is instead of storing everything cubically, you're just going to store values where you're close to the surface. And the idea here is that you would
like to have a very fast function that gets you from a 3D coordinate to 1D index in a lookup table. And this is the hash functions here on the bottom right. It's just basically taking the coordinates times a prime number, XOR times the next coordinate plus times the prime number, XOR times the next coordinate and the prime number, and so on. So it's really, really straightforward. And on a GPU or so, you can do these things, well, without even thinking, right? This is just a bunch of arithmetic operations that a GPU can do very efficiently. And this way you can basically go to kind of like infinite resolutions, right? So you have this unstructured hash table that can store your scene, and you're not bound to any spatial limitations in a sense anymore, because you can also start streaming this linearly. You just, every time you look up a coordinate, you just run the hash function and check what's the current value there. And this is the thing what people use today as well for 3D scene understanding. So like Minkowski nets, sparse convolutions, they all kind of use the same idea. So you kind of have this hash table and that stores the scene representation. And then every time you're making a query, you go in this indirection via the hash, which is very cheap to compute in order to make a lookup. And we could actually get pretty decent reconstruction. So this was, again, this was a real-time reconstruction at the time. It was like 2013. So that's like 10 years ago right now. So it's already quite a while. So I guess, yeah, I'm getting older too. And you can get very large reconstructions like these ones. And at the time being, people were actually trying to still figure out, so we're not quite at, you know, super point, super glue land right now, what we have at the moment for registration. We had really trouble at the time for getting frame registrations running at the time. And everybody here was using some frame to frame or frame to model ICP version. So you have a geometric point to plane term that you're using to align the depth maps to the respective model, and you kind of iteratively do this as you're getting more and more depth data as input. And this is relatively easy to do, and it's obviously there's a lot of seminal work around various ICP variations, but the downside is if you're doing this in a real-time setting, you're gonna get results like that. So you're gonna get these loop closure problems where you basically, you start at one point, right? And as you go, you accumulate error, and this error accumulates. And if you revisit the same point, you're gonna have this issue at the end. So there's no bundle adjustment happening, of course. There's no global post-optimization, what state-of-the-art SLAM methods would do today. And we, at the time, we thought about doing this in the context of RGBD data, and we worked in this bundle fusion work. And at the time, this was now a few years later in 2017, was one of the first works that could actually do this kind of stuff in real time. And it's not quite bundle adjustment what we're doing here. So what we're doing here is we're still using SIFT correspondences to find matches, but we're assuming we have the depth given by the respective depth observation. So the bundling comes a lot cheaper right now because you don't have to estimate the depth basically, right? And the term is pretty straightforward. So this is just a non-linearly squares term. But what's nice about this, these kind of terms, you can run very quickly with Gauss-Newton, Lemberg-Marquardt solvers, and you can parallelize this very efficiently on the GPU. So at the time being, we had kind of this hobby that we had was we tried to go ahead and make GPU solvers with these second order methods like Gauss-Newton and Lemberg-Marquardt for all kind of problems. And it was really fun. It's still very difficult actually to do this even today. So you can be much, much faster than what PyTorch and so on is doing right now if you're hacking your CUDA kernels accordingly and leveraging the memory in the right way. And yeah, so if you can do this, you're basically going from having this reconstruction to this reconstruction, right? So you can do online correction of your poses. And in 2017, like this was kind of a relatively remarkable achievement because you could get like real-time correction of your reconstructions. And we did a little bit more. We did a way how to update the scenes on the fly. And you could do demos like these ones. So this is captured with an iPad and structure sensor. Structure sensor is kind of like a Kinect on an iPad. And what we do here is we stream the data to the computer. You start the scanning. Now it's streaming it. You see the live reconstruction. And yeah, you can go around and do 3D scanning now in real time. And on the bottom right, you see the reconstruction here. So for the visualization here, this is actually a raycast of the sign distance field. It's not the marching cubes. This is typically what you would use there. And now you can see that, like the bundle adjustment will kick in once you complete the loop closure. So you still see there's a little bit of error that was accumulated, but now it's updating the scene reconstruction as you go and find the respective matches in your pose estimation. And you could even do things like relocalization at the time. You could go ahead and block the sensor, right? So now the sensor is occluded. And then you basically use your SIP matches in this case to figure out how to relocalize. There's a ransec involved to do that, and you recover the tracking on the fly. Yeah, and then you can, revisit the areas, and the more you scan, basically, the better your reconstruction gets. Also, the better the poses get. Yeah, and then at the end, you run your marching cubes, and now you have meshes output. And you can get pretty good reconstructions with that. So this is something we scanned because we have this interactive feedback, right? You can basically navigate around, and you can see and get relatively complete and dense reconstructions. And we've used this for quite a bit. So a lot of people might know the scanning data set or so. This was built all on this kind of framework, and we're still using it for a lot of research projects, actually. So even today, well, while it might not be the best pose estimator and the best SLAM method anymore for reconstruction, still a lot of people actually use it. But now I want to talk a little bit about what we do with this, right? I mentioned we use this for ScanNet, we use this for semantic scene understanding, and we kind of build a 3D deep learning environment around these kind of 3D scans. But now I want to talk a bit about the feature matching, because that's what I promised and what the spirit is of this workshop. What I'm very excited, generally speaking, is using the 3D data for self-supervision. You can do a lot of cool things. And the obvious thing, and at the time this was kind of new, was you can learn matching key points, right? Like matching key points in let's say 2016, 2017 was kind of a new thing that people started to explore with deep learning methods. And generally speaking, when I talk about self-supervision here, the idea is this red point that you see here in the scene, you see this point for many views, right? So you get for free training correspondences. So once you have a good reconstruction, right, you have training correspondences to see this point from many, many other views. And that's cool because now we have correspondences that we can use for our favorite neural networks, and we can start training all kinds of methods around it. And what's nice about this idea is because we have this constraint of a rigid camera pose, we can even think about it this way. Even if we have bad feature matches at the beginning, bad correspondences at the beginning, we can just select the ones that work, use those ones for training, and then iteratively get better and better correspondences as we go. Because again, to align 2 frames in an RGBD frame, you only need 3 correspondences, and that's basically it to get the pose. You want to have a few more to be more robust, but in principle, that's mostly it. And what we were very curious about, we were curious, can we actually learn these feature matches in 3D? So not in 2D right now. This is, I understand a lot of people here work on image matching. We thought about, can we learn these things in 3D? So we had this 3D match paper in 2017, which basically was one of the first papers in 3D to actually use deep learning to learn correspondences. And the core idea is, well, you needed some sort of 3D representation, right? In image space, it's pretty easy because you have a 2D patch. So here we needed kind of like a 3D patch to match. And a 3D patch to match in this case was just a local volume with a bunch of signed distance values where we trained a neural network to match it. And well, the training data we have right now from these data sets we constructed, right? Existing 3D reconstructions where you can self-supervised extract various matches. And no, this was like a pretty standard architecture, what you would say today, but at the time this was pretty new. So you can now go ahead and form these. Well, in the end of the day, we tried various versions, right? The easiest version, you just have a metric learning network. So you have kind of the Siamese tower here in the middle, right? And then you have a metric learning network at the end to compare the 2 features from these towers. Both of these towers, they encode the respective features for each of these 3D patches of the signed distance fields. And then you have this matching network that compares it. And actually, we tried a lot of these different versions, right? I mean, this is also no magic anymore. Like this is pretty standard in today's pipelines. You can start with L2, you can start with triplet losses, and later on, I'll show you a little bit more what we can do, for instance, with contrastive losses here as well. Yeah, at the time, we actually had to scan scenes to specifically capture data. I think this is still being used quite a bit, this 3D match data set that we created there. Of course, it's not at the scale of like modern data sets, like ScanNet or Matterport 3D and stuff like this. But at the end of the day, you're getting actually pretty good matches. So here at the time we compared against state-of-the-art, at the time state-of-the-art feature descriptors in 3D. So we had spin images was very popular. You can lift to 3D. This FPFH, this is basically a histogram of normals. Or you can do 2D continent actually. You can do a 2D continent on the depth data. And we show basically that if you're doing this in 3D from a distance field, this was very good. So of course, I'm not arguing this is state of the art anymore, right? Of course, you have much, much more powerful networks right now. You can use larger architectures. You have better types of architectures. You know, modern inception net architectures would be a lot better than this one. But it was kind of nice. It was very straightforward to train. And we showed that if we're doing this, we actually also get good reconstruction results. So we could kind of augment our existing pipelines, which at the time used CIF matches. We could augment this with 3D matches. And you can see that more matches you had, obviously, the better reconstruction results you got. And, you know, there have been a lot of developments around this, but I think the core concept of learning features is still pretty similar in this case. And people, especially, I mean, I'm still working a lot in the 3D domain here. In the 3D domain, people pretty much follow these pipelines. Okay, I mean, the losses changed a bit, the architectures got bigger. The way you sample your training data changed quite a bit. And then obviously how you do the matching at the end of the day between the features, like, you know, at the time that people were using Ransack, now we have much better versions that a lot of people here in this room actually have also. But now I want to show a few more alternatives of this one here. So this one is for feature matching and very basic, right? Very straightforward. But it turns out you can use this also for other tasks. You can do the same tricks that people use for feature matching itself. You can use the feature matching features that you're training here generally for representation learning. And this is one thing we've been working on a little bit. So there's a couple of core ideas, right? So the core idea is still the same. The core idea is you have a 3D reconstruction. From the 3D reconstruction, you have RGBD images that are aligned. So you have the poses to it. And we treat those as pseudo ground truth. And you pretty much know that they're ground truth because otherwise the reconstruction wouldn't look very good. It doesn't have to be even perfect for a lot of the applications, what I want to show here, but it has to be good enough that it's not like, you know, horrible pose misalignment and so on. But the idea now is essentially that you can go ahead and use these correspondences in 3D for representation learning frameworks in order to get very meaningful features to then do some downstream tasks. And there's different types of downstream tasks. So in this slide, you see here, like I mentioned, 2D downstream tasks, you know, like segmentation, detection, instant segmentation, and so on. So it turns out that this is actually super useful for a lot of things. And you can do this without having any labels. So for instance, if you want to have your 2D segmentation network to be trained on a large set of data, you could just use a multi-view or RGBD data set in order to pre-train features. And well, why is that useful? And the main argument that I'm making here is basically, if you want to do computer vision on a 2D image, the whole point is you want to be few invariant with your networks, right? Like, it doesn't matter where you look and how you look at a certain thing, you still want to get pretty much the same feature, right? I mean, that's kind of the whole point. So this is like trying to take one part of the invariance that you would like to learn out of the equation in 2D learning methods. And the way we're doing this is with the contrastive learning framework. So in this case, assuming we have a 3D scene, and now we simply, well, let's start with learning 2D correspondences, right? So we have here two viewpoints. We have an image here. We have another image here. And of course, we can just, you know, take all of our points here in this image where we have key points, for instance. We can take these key points and establish correspondences between them, right? We get that for free from the data. Okay, we have to check that there's a depth value for each of these image pairs, for each of the points in the image pair, but otherwise it's pretty straightforward to do. And this one gives us free correspondence in 2D. Same thing what we have done before, except now we're doing it on, let's say, 2D patches. You can also do the same thing for 2D, 3D pairs, right? I can just take my 3D scene, I have like a corresponding 3D patch. So it's like, again, a small voxel grid with a signed distance field in it. I can go ahead and match it with an image, right? So I have a bunch of correspondences here. And based on my reconstruction, based on my registration, I know precisely where these points should match. Yeah, and now we can formulate our favorite representation learning framework. In this case, as I mentioned, we're using a contrastive loss. And the whole point of this contrastive loss right now is to learn features in a pre-training pass that are few invariant, right? So we have these two color features. We have these two color images. We use a 2D backbone. We use shared between those backbones. And then we match the features. And then we say for every pixel in this case that matches, we have contrastive loss here. And these networks right now, you see this is a nice CVPR paper from 2021. Here we already used pretty much state-of-the-art architectures. Even from today's standard, these were relatively large backbones that we used. And the whole point of this whole thing here is just to have very good pre-training for these 2D backbones here. And then basically the idea is we want to train these networks, right? We want to pre-train those, and then we're going to chop off the contrastive loss. And then we're just going to use these 2D backbones and we want to use them for downstream tasks. So in a sense, we're competing kind of with like ImageNet pre-trained networks here. And we'll show you that if you're doing this, you can actually outperform pre-trained ImageNet networks, which is kind of nice. But we can do more. We can do this 2D, 3D thing, what I mentioned before, right? We can say, oh, I'm gonna have a geometric prior here. So I have 2D and 3D correspondences. So I have a 2D image here. I have my 3D geometry to it. Now I'm gonna have two different encoders though. I'm gonna have a 2D backbone and a 3D backbone. And so obviously you can share the weights between those two, right? Because they just have different modalities. And you can have also contrastive loss here, right? You can just say, oh, well, you know, these features or these feature points that I'm mentioning here, they should have the same features when you extract the features respectively. And the whole point of having this contrastive loss here is still the same as before. The only thing what we care about here is this 2D backbone. We just want to get good features in 2D that we can then use for the respective downstream tasks. So this 3D backbone that we're using here is kind of a proxy helper, right? It's just here, just for the pre-training. For the fine-tuning later on for the 2D backbones, that's the only features we care about. Or that's the only network we care about. Okay, and now we can combine these ideas. We have two of them now. So we have 2D contrastive losses, and we have 2D, 3D contrastive losses. And if you think about intuitively what should happen here between 2D and 2D, the idea is that we're learning few invariants, right? So we're saying like, no matter when you look at a point, it should always be the same feature. So you should be few invariant irrespective of the current viewpoint. And the geometry prior also has an intuition. It says basically, well, please make sure that my image features are close to the features that you would get from geometry. So it's kind of like forcing a prior to get some understanding of 3D shape, right? But it's very local. It's not like the whole scene. Like the context here of 3D is not that large. Okay, and now you can train this. And now what we're doing at test time, or like not test time, but at downstream task training time, we only use the weights of this 2D backbone, and then we can add our respective heads to this network that we want. So for the easiest thing is a 2D segmentation loss, right? A more complicated one would be something like, I don't know, like mask RC and doing 2D instance segmentation. So your region proposal network at the end. But the whole point is we want to use these pre-trained features. And now what we show is, for instance, here's an example on image segmentation. We have here a bunch of comparisons. So the comparisons what we have here is, so we have two data sets. We run this on Scan and NYU. We have different baselines. So we have ImageNet. So ImageNet means you just pre-train an ImageNet and then you take the backbone, you pre-train an ImageNet, and then you fine-tune respectively on the target dataset. We have MoCo. MoCo version 2, we tried all kind of versions of MoCo. So we have a lot of applications on MoCo here in the paper. But the core idea is pretty similar, right? So you have basically a pre-training network that is used for representation learning, and we're trying to use that as baseline. And then we have ours where we have Pri 3D, only the view features. We have Pri 3D with only the geometry feature. And we have the combined version. Okay, now let's have a look. Okay, so this is ImageNet. This looks like that. Yeah, this is ImageNet. This is ours. And you see that, you know, like it just looks better. I mean, obviously, this is just a few samples. But you see, on average, we're getting actually better results with the pre-trained ImageNet version. And I think that's kind of remarkable. So by just using like kind of a 3D feature matching self-supervised training like signal, we can actually get better results than if you're using kind of state-of-the-art pre-trained networks with ImageNet. Okay. We also quantitatively evaluate this. So this is the famous table 1. So in this table, we have 2D segmentation results on ScanNet. And you see a lot of applications here. So if you basically, so we tried this also on different backbones. So here we have basically ResNet 15 and ResNet 18. So if you look in here at the top, this is training from scratch. And training from scratch gets you relatively poor results. The reason why they're poor results is because the fine-tuning data set is not large enough. So if you have a larger data set to pre-train, obviously that's going to work a lot better. So if you use ImageNet here, obviously you get a massive performance. I mean, this is what basically deep learning has shown for the last 10 years, that this kind of transfer learning works really well once you have a pre-trained network. And then we try a couple of baselines. So I think all the MoCo variations, they give like 56 MIU here, or like 56 better versions. Obviously, it changes a little bit between the smaller ResNets, but then we see that we have a consistent improvement here towards even MoCo, right? So compared to like, ImageNet pre-training only, and compared to MoCo, we're actually getting like, +5, +6 MIU here with respect to the downstream task performance here. And again, the correspondences come pretty much for free. We do the same thing for instance segmentation, same thing, we do this in ScanNet as well. Again, you see here at the very top, you see training from scratch, right? You see the numbers are relatively low. You see ImageNet pre-trained, that already gets you quite a boost. MoCo improves on this one. I mean, the whole point of MoCo was that you could actually improve up on ImageNet pre-training. And then you have, all of our ablations again. So view only gives +1.7, plus geometry only gives +1.8. And we show that these two actually help each other. And at the end of the day, we're going to get +3.2 on the evaluation here in terms of the AP scores. And I think that's pretty cool. That's pretty remarkable. The only caveat here is this is evaluated on ScanNet, right? So ScanNet maybe in 2D is not the best evaluation. So I understand that this is a fair criticism. The only challenge here right now basically is, well, you need some training in 3D. So you need basically so the argument what we're making here right now, instead of having labels for pre-training such as an ImageNet, give me a multi-view data set with some 3D correspondences and see how much pre-training you can do. That's kind of the competition you have here. So we tried this a little bit on other data sets like cityscapes and Kitty and so on, and this also worked in the same spirit. Depending on the data sets, it's a little bit more tricky because the data sets might be a bit too small. Like cityscapes, for instance, was a little bit too small for this case. But but the same concept still applies. And I'm arguing in the long run, I think computer vision for the most part doesn't have single image input. For the most part, you're going to have at least some videos and real applications. And as you capture data in like self-driving car scenarios and stuff like this, you can actually get this to a reasonable level. But again, it's a little bit of a different roadmap than using existing pre-trained networks. Okay. So yeah, this was basically using the feature matching for downloads. Now I want to show one more work where actually the question is correspondences a little bit. So I want to go back to this feature matching. So previously we have seen feature matching mostly works along the lines of, well, you're going to have two images, right? You do a bunch of feature detection. You're gonna match those. Well, you're gonna run a feature extractor. You're gonna match those features, and then you're gonna do your favorite like structure for motion method or SLAM methods or whatever in order to get some poses at the end. And now I want to go the other way around. So like in this previous work here, right, we have shown that using the feature matches, they can help downstream tasks. Now I want to go the other way around and want to show, can we actually use semantics to find better correspondences as well? Well, I mean, the obvious thing is to use pre-trained networks and use larger architectures, what people have been doing. But that's a little bit too simple. I want to go even more higher level. And I want to show this one paper from this year's CVPR, actually, which we call object match. And the standard way, I mean, as everybody knows, for conventional feature matching is we're relying on two views that have overlap with each other. So, right, so I have two images. And what you do is you detect a bunch of key points, and then you're finding, in this case, this is running superglue, right? It's trying to find correspondences between those two images. But the whole assumption of modern SLAM SFM pipelines is that you have overlap between images. And this only works well if you have enough overlap. I mean, okay, I mean, state-of-the-art benchmarks, they try to take this to an extreme with like crazy viewpoint changes, because otherwise we wouldn't have stuff to do anymore. But this is kind of the high-level idea, right? And this works. And at the end of the day, you're going to get reconstructions like these ones. Again, this is still for like RGPD case because, I personally care a lot about 3D reconstruction. For me, that's one of the things. But it doesn't matter on the downstream application. The concept is always the same, pretty much. And what I thought what would be really cool is, assuming we did have some notion of geometry. If we had some notion of geometry, I can also figure out correspondences where we have low overlap, or even more extreme, if I have zero overlap. And the idea here is that you basically do something that is object-centric. So if I get a notion of an object, and I kind of use the object as an indirect virtual correspondence, I just leverage the semantics of the object to find more correspondences. To give you a more extreme example, if a human looks at a chair from one side and then looks at the chair from the other side, as a human, I can pretty much guess how the camera poses have changed, even though there's zero overlap between the images. And the only way I can do this as a human is I just have the objects in the center. That's very straightforward. I know that there's an object. I know roughly the object shape. And based on the object shape, I can establish these indirect correspondences. In this case, we're going to call these object correspondences. And I want to make this a little bit more clear what I mean by object correspondences. Of course, the challenge right now is for a method is each object has a different shape. You don't know the shape necessarily. And shape estimation by itself is also, not solved is maybe, we're far away from that, right? It's like, it's just not at that level. However, what we're pretty good at is we can basically think about mapping these objects to canonical spaces. So just think about it. Each object is just a bounding box. You have a 6-dot pose or even a 9-dot pose if you consider the scale for the objects. And then you're mapping each of the objects to this canonical space. So now I'm changing it from finding a point on the surface on the object. I'm just trying to find where does every observation from the object map to this unit space. And this is a thing what people call normalized object correspondences, NOCs. This is being used for quite a bit in the 3D community, actually. And so if you're looking at the method overview here, we're thinking about a method like this. So assuming we have 2 input frames. So from these 2 input frames, what we're doing is we're first detecting these NOCs. And again, these NOCs are basically being trained such that each object maps to a canonical box. Okay, to be a bit more specific, what we're doing here is using scan2cat, which is a data set that is on top of ScanNet that has CAD models. And all we're trying to do is for every pixel, we're trying to figure out right now in this image, where are you in this 3D canonical object volume? Right. So in this case, you don't need to know necessarily the object by itself. The network still has to figure out just this mapping from object to canonical, so from pixel to canonical object coordinate. And it's actually not such a hard task to learn if you think about it, right? Like if you see that the bottom left of the chair, well, that always maps to the bottom left of this volume, and the top right of the chair maps to the top right of the volume. There's a couple of things that make these NOCs, these normalized object correspondences, not that easy to deal with. So for instance, there's symmetric object that is not so easy. And there's different types of symmetries, right? You have rotational symmetry, you have reflective symmetry. So there's a couple of ways how to deal with that. But in principle, it's relatively straightforward. And again, the way how we train this, we basically take scan2cat. So scan2cat means we have 3D reconstructions, images, and CAD model alignments on top of that. And that means for every pixel on an object, we know what the respective canonical object coordinate is. Now we're just using a large 2D object, like an instance segmentation backbone, like we're running an instance segmentation. From this instance segmentation backbone, we now, for every detected object, we have the mask, and the mask just predicts the respective NOC coordinates for every pixel there. And this is what you see visualized here, right? So these colors here are just X, Y, Z coordinates in this canonical object space. That's all that we're doing here. Okay, and now what we want to do is, in order to find this useful for any SLAM or SFM method, now we have to also figure out, when we have an image, we have to also figure out how we do object identification. Meaning we need to match objects first, right? So now what we do is we have, let's say, 2 images. For each of these images, we run our object detector or instance segmentation. We get these NOCs based on the instance masks, and we also get the bounding boxes. And now what we do is we're going ahead and computing a feature descriptor on a per object basis. So in a supervised way, based on a data set like that, we can now figure out which object matches over time. I mean, this is not matches between frames. And that's not so complicated, right? Finding object matches, that's pretty reasonable. And you can do the same tricks actually what you do for low-level feature matching right now. You can do run like a ransack to match the objects accordingly. So it's pretty straightforward, except that it's a lot easier because even, how many objects are you really going to have in practice? I mean, you have like, I don't know, like tens of objects maybe, or like 5 to 10 objects per frame here. And then what we do is we adding these correspondences to a global optimization. And this is what's happening here. So here we have basically a couple of terms here. So if you look at this, so we have 2 terms. This is the first term. This is just the kind of a RGPD bundle term. Like it's just for every point, you have a transformation to the other frame and match it to the other point, right? This is just matching 3D points between frames. This is a least squares problem. Again, you have here over the frame pairs, over the pixels, and over the other frames respectively, right? Sorry, this is over the pixels, this is over frame, and then frame pair ij basically, right? And the optimization here optimizes here for the TC in this case. We're also optimizing for the depth, depending on whether we have depth data or not, whether it's a true bundle adjustment problem or not. And then here's the interesting part now. This is the part here where we go in this objectness term. So now it's very straightforward. All we're trying to do right now is like we're kind of introducing these virtual objects. So every object by itself gets a 6th of pose. And all you're doing right now is you're matching every pixel from these knocks with the objects itself. And now you're jointly optimizing for the poses of the frames and for the objects of for the poses of the objects, right? And then like you get correspondences from a frame to the object, and then from the object back to the next frame, and so on. And the objects in themselves serve as anchors here. And the nice thing about this one is you don't necessarily need any overlap between the objects itself, right? Because like one frame might just match to features from the might just match to points in front of the object, and another frame might just match to points in the back of the object. But because there's only one transformation for the entirety of the object, and you know it's the same object based on the object matching term, you still get this correspondence. You can get loop closure without having a loop closure, basically, right? Okay, and then yeah, I mean obviously we're just adding these terms together, and then we're jointly solving for the frame poses as well as the object poses, and potentially for the depth if you need to, if it's in the true bundle adjustment setting. We did, however, focus mostly in the RGPD setting because that's what we cared about in our application. But the whole concept of adding these like virtual correspondences is pretty straightforward. Okay, yeah, and then you optimize everything together. Okay. Yeah, then we have here, we can do pair-wise registration. So these are a couple of examples that are more extreme cases, right? So, I mean, what's going to match here, right? If you're looking at these 2 images. So I think traditional feature descriptors would have real trouble here. But if you do an object detector, you would detect this object, you would detect this desk here as well. And then you know that these 2 are basically matching, right? And yeah, and this way, then we can basically align frames with these ones. Okay, I'm gonna have a few more here. Same thing here. So what's matching here? Here we have these objects here matching. Well, this one goes a little bit in the wrong direction, right? But if you see the same thing here. This cabinet or whatever it is matches with this cabinet, and then you, based on the object detection, okay, you have to rely on the object detection, right? That has to work, otherwise this doesn't work otherwise. But then you get these correspondences, and same thing, then you can align these 2 frames. And I think these are problems which are pretty difficult otherwise to do. I should say, however, I'm not claiming this is an independent structure from motion method or whatever. I'm just saying this is a thing, these features you can just add for free all the time, right? Because they're just additional features that you otherwise wouldn't get with any method that relies on direct overlap. And then we're evaluating this a little bit in kind of a couple of settings here. So this one is mostly done with still RGPD data here. This is still on Scannet. And we have like the very standard baselines here is SIF plus bundle fusion. This is like the method I've shown you before. Again, I'm not claiming these are the best methods ever that are being used here. You could probably engineer this better, but this is more like to bring the point how much these correspondences help. And the main thing what we want to evaluate here in these tables and in this graph is what the overlap is going to be. So, right. So if you have more overlap between frames, then the method, I mean, it doesn't hurt, but it also doesn't help that much anymore because you have enough frames to do post estimation anyway. If you have less overlap, at some point you break down. I mean, the extreme cases, you have zero overlap anymore. Right? Like in principle, you can still do pause estimation if you have zero overlap in this way, right? Because you have the objects at the center in the whole optimization. Yeah, and basically here you can see the different variations here. Which one should we look at first? Well, ours is the blue one. It's obviously this one on the top, which is the best. That's kind of the point, otherwise you can't publish a paper. Okay, and then we have basically, okay, this is just the geometric transformation, then you get a little bit worse, right? You have various ablations. We have the object tracks here alone. We have this one's just this is the standard global registration. You see at the end of the day, it gets as good as ours, right? But then you have enough overlap again. And if you look in here on this regime here, you have the same thing here, right? Basically, this is like with less than 10% overlap, then you see dramatic differences between the respective post recall here. Oh yeah, for the post recall, we're using 30 centimeters and 15 degrees, which is fairly lax metric. I mean, this is just for the sake of the evaluation. But you see basically like none of the methods work in this regime unless you have these indirect correspondences, which is obvious, right? Because again, you have no overlap here. Okay. Yeah, and then you can basically do standard SLAM, right? You can go ahead and run the method, you get more correspondences. Because of more correspondences, you get better loop closures. You get these nice correspondences here between the objects. Yeah, and here, this part here, we get a few more here. And you can do the same thing here. Right, same thing here. You find basically this one between these chairs as well. Yeah, we're evaluating a bunch of SLAM sequences. So this is on TOM RGPD. Note, however, that we're cheating a little bit here. So we're having basically a lower frame rate. So we artificially making the benchmark harder by removing a bunch of frames, because otherwise the benchmark is pretty explored. Otherwise, it's pretty hard to make a lot of progress on it. And yeah, same thing right now. Basically, if you have very little overlap, all the baselines fail because you don't have enough correspondences. This is also on ScanNet with also relatively little overlap. You also see that all the baselines basically all fail pretty much. Okay, yeah, so I think this is really cool, and I think this is basically, in my opinion, one of the futures of like SLAM and SFM. However, there's a bunch of disadvantages. I think one disadvantage there is basically that well, you need some data set to train these correspondences. This is the big downside. So you need this training data basically. The way we do it is ScanNet plus scan to cat. That works on these indoor data sets, but on outdoors, well, I guess Kitty has some cat annotations, but then you have like one object category. So the question how to channelize this, I think is still pretty interesting for future work. Yeah, so this is a paper for this year. Like if you're interested, check out the poster. And with that, I'm mostly concluding. I've talked a couple of things here in this talk. Well, obviously, learned feature matching has gotten a lot better. Like Eric has shown a lot of cool stuff in the previous talk. I mean, how we generally speaking, like develop the whole pipeline right now of modern pulse alignment. Like when we started this in like, I don't know, 10 years ago, this was like really basic and really actually not working at all. And then people started to cheat a bit, use visual inertia, but now with deep learning, I think you can actually get pretty well. I think semantics plays a much more important role, and I think this is still a big, I don't know, I just care a lot about this because this is, I think, how humans do it. Like humans can do pulse recognition where like you don't have overlap. And this is something I feel we're missing still in a lot of these SLAM systems. And yeah, aside from that, I think self-supervision is still pretty awesome. Obviously for feature matching, that's pretty standard. Like everybody uses this right now. This is not like a huge magic pony trick anymore. But I do think there's a lot of other things you can use like this representation learning stuff, I think is still pretty cool. How you can leverage these features, possibly in device architectures that make use of this. Like capsule networks was kind of an interesting conceptual idea, right? Where you can kind of incorporate those ideas of like how the 3D scenes are formed from 2D. And that's very similar to leveraging like 3D scenes then for supervision. Okay, with that, I'm pretty much at the end. These were a couple of papers I talked about. I really want to thank all the students and the collaborators. With Angela was working on the bundle fusion. 3D match was done by Andy. Prior 3D was done by Chi. And object match is done by Chan. So if you're interested in that one, again, he's here and you can talk about it. And thanks to my group. And hopefully we have still time for a few questions. Yeah, thanks.
Thank you. We are a bit over time, so I'll ask one question from Zoom and one question from somewhere. So from Zoom, the question is, in one of your previous work on Giraffe, the 3D presentation was latent in encoded feature space. So can it be possible to find the contrast in some latent space in order to bypass the need of explicit 3D presentation?
I'm not sure if I fully got it. Sorry, which one is that actually?
It's in chat. So, and it's like last one in chat.
Oh, the last one?
Yeah.
Someone supposed to find the contrast in some. Oh yeah, of course. Yeah, I do think so. I think basically the question is, can we use contrastive loading on the latent spaces? I think, yeah, of course. I think this is a really cool idea, and I think that might be very interesting. The thing why, yeah, thanks. Yeah, so basically, actually, honestly, this would probably work better than what we're doing. I think this would be a better version of what we have done in Try3D, because I think you can basically have better architectures to specifically tailor to that. So yeah, you should do that if you can, because that probably gives you better results. Yeah. Yeah, I guess we can just start.
Thank you for the presentation. I have two questions. Can you elaborate a little bit more on
One
question?
Yes.
Okay. Elaborate a little bit more about feature matching for representation learning, and what do you supervise in view invariant compressive loss?
Right. So the supervision just comes from different viewpoints. You see the point multiple times. And by adding to making sure that no matter how you see it, it gives you the same feature, that's the supervision. And then you can have different multi-scale resolution and stuff like this. You have different types of patches, you have different types of 3D patches, and you supervise them respectively with 2D. Yeah. Should we just go through it quickly, or is it if you?
Yeah, like let's like finish this line. 3 questions.
Okay.
Okay, great talk. Thanks a lot. Yeah, I do agree that including more semantics and 3D for matching helps a lot. For the last work on object match, have you considered adding like the Knox information to extract in the matching process itself, kind of maybe learning an end-to-end way? Like I see like these are different disconnected components in a way. They seem to really help, but yeah.
Actually, we're doing that. Actually, you can differentiate. So we tried that out. So we can differentiate through the, so it's kind of funny. So what you can do is the pulse estimation, like structure motion, is differentiable. You can differentiate through that, and then you get gradients through the Knox as well. It's very basic what we're doing there. I think you can go with that because like with PyTorch, it's super easy to get the structure from motion stuff differentiable, and then you can get the gradients to it. And I think that's what you want to do. I think that's a really good idea.
Cool. Yeah, actually, I have a paper from my group that is adding Knox with superglue in the learnable matching process. So it's very related.
Absolutely. Yeah. Cool idea. Like it.
Thank you very much for the presentation. Yes, it was a very nice kind of transition going from the feature matching to object matching. I was wondering if you have considered going even beyond that to include more context, such as like surrounding objects, background, and other features together.
Yeah, absolutely. Yeah, absolutely. I think it would be nice if you had like a full scene graph and had relationships between the objects. And I think that's missing. But it's also, this becomes harder to train because there's not so much great training data anymore, right? Like, but I think that's the way to go in practice, because like when I'm closing my eyes, I'm thinking about relationships between objects, and that's not considered here in a sense, right? And I think that would really help a lot and to give you more structure. Yeah.
Okay, final question.
I'm wondering what happened in this room if you do the object matching with 200 identical chairs.
So we have identical chairs. It's doing a ransack on a per object basis, right?
But I mean, like we have really like each object. I mean, hundreds of identical chairs in this room. How the object matching works.
Right. It becomes obviously a lot harder. But like this room is an extreme case right now. But what I'm trying to say is like in this room you have a bunch of chairs here where sitting people on it and a bunch of objects on it, right? So in this case, the object matches would already tell you, oh, these might be different ones depending on how you train it. And then you have to rely on your ransack, basically. You have to make sure that this works better. I still think what would be better here is to have like a graph matching network or so that considers all kind of relationships. But obviously, that's like a hardcore extreme version of this right now. Not claiming this is the best case to do it. But I still think you can still get some signal out of it. I don't think it's completely lost.
Yeah, let's thank speaker again. Sorry, we should have some very short coffee break, at least like 5 minutes. And then we get back with paper talks and then challenge winner talks. So see you in 5 minutes.
I think he's here, so you can just ask him directly.
Hope I didn't go too much over time.
Oh, that's okay.
Okay, I'm gonna leave this in now.
Yeah. Oh, I need to share screen now.
Thanks for organizing.
Thanks for coming.
Yeah, thanks. I didn't want to talk about nerves, so I had to do it. That was perfect. I mean, it's kind of remarkable, like how far modern people describe the match also actually.
Yeah, actually, I would like to like ask the same question as Daniel. Like the problem, like with things you're showing. Okay, there is a desk, and imagine there are like two desks, and like you don't know which one do you see now. And like in image, you have one. Like for SLAM, it's probably because they have sequence you can read, but for SFM scenario or like R scale, and if you register a wrong image, your reconstruction is killed basically.
Right. Absolutely. But if you only have two, that's another big problem, I think. The two you can figure out, you can handle somehow.
How? I mean, well, you have image with a desk and image also with a desk, but they're actually different desks. Like because they are two, but you don't know that.
Right.
So what do you do?
Well, you try out, right? It's an optimization. So based on you add to the optimization, you try this combination, that combination, you get a different error in the post. And based on that, you're selecting which one's for the better.
You haven't yet added. Like you have photo of that, right? Right. Maybe. Okay, fine. That's photo with another desk, but you don't know this, and you actually don't have the second desk yet in your reconstruction.
No, but I'm talking about like for the global part after. So if you have all the images at the same time, then you can do it. What happens if you do it sequentially? What happens if you might make a mistake, right? But you still have the standard blend stuff that gives you the error, right? So if the error goes up, then you would just start it. I don't know. It's the same thing as a key point, of course. But I understand if you have too many wrong ones, at some point you're going to fall apart. I understand that part. And like this room would be, of course, not easy.
Like probably you just zoom out maybe, and then it would be.
I mean, I think what's missing is like it's partly related to the question. I think if you have enough spatial context, then you can actually just differentiate between different objects in the room.
Yeah, I also build scene graph.
And you build a theme graph, you have a relationship, then it's easier. Like we don't do that.
Yeah.
Like for us right now, this chair and this chair over there, from a feature perspective, an object matcher is identical, which is an issue, of course. I get that. But if you have like a full theme graph, then it would be easier again, right? Because then you know, okay, this one was here and this one was over there, so you don't even have to consider. So we do this only during the ransom, but not during the matching. So if you have like a graph matcher or something like this, that does all of them at the same time, then I think you can address these.
Yeah, but I'm also ready.
Haven't done that, but
okay. Yeah.
But I think that, in my opinion, that's still the way how what's missing in current SLAM methods actually. Like because there's no semantics.
Yeah.
Like we're just tweaking it right now. Like how far can we push the feature descriptors? Yeah, amazing, it's great. But I think this like scene graph build and so on is not. Yeah, is missing, right?
Yeah, I think I have seen some kind of work on semantic SLAM, but it was like very few of them.
Right? The problem I think in practice is still the data, right?
Yeah.
I mean, you can still criticize the same stuff.
Yeah, you have scanned it and what else? No.
And that's it. I think there's like Kitty has a bunch of them, but it's very few.
Yeah,
right? You just don't have a lot of it.
So we have everything now on slides.
Oh, okay. Oh, sorry. So, about here. Okay, unmute. Sorry for this.
Is that from the beginning?
Meeting if somebody doesn't speak on mute.
Yeah.
I mean, slides are nice, aren't they?
Yeah, they are. Okay, sorry for this.
So yeah, I guess you've seen the video. Didn't get much of that, but there's not much to get to begin with. But pretty much what the robot was trying to do at that point was localize, and it's a task called visual localization. I'm pretty sure everyone knows about this, but just for the sake of completeness, given a query image, you want to find where this is in space. First, you process that with some model, some algorithm, something, in this case represented as the neural network. And there you get key points and descriptors or interest points within that image. Then using those, as well as a 3D map, you're able to find roughly where the 6-degree of freedom pose is. Now, we talked about robots and mobile devices and so on. And of course, to use these in such platforms, we need them to be efficient. And what I mean by efficient in this case is we need to be able to extract the key points and descriptors in real time and also localize within the 3D map as fast as possible. In this step, we try to address both points. First, let's talk about making the networks faster. And for this, we explored network quantization. So specifically, we propose layer partitioning and traversal strategy. So what is this? Starting from any interest point detection and description network, we group the different operations into what we refer to as macro blocks, depicted in different colors, and then iteratively find which is the optimal quantization strategy for this. More specifically, what I mean by this is starting from a baseline. We first find the optimal quantization strategy for the first operation, for the first macro block in blue. Then we move on to the one in green, and so on and so forth until we reach the end of the network. Now, what does this mean number-wise? Remove most of the numbers, but compared to the baseline on the very, very top, and our method after fully quantized at the very, very bottom, we achieve comparable performance, but being an order of magnitude faster. So what was the second part we talked about? That is the descriptors. And specifically, we're interested in binary descriptors. Now, this is a hard requirement for many applications, and hence why we opted for this extreme scenario. And for this, we took inspiration from metric learning. Specifically, in those cases, you always use an auto-normalization for the descriptors. And we asked ourselves whether we can find an equivalent for binary descriptors. This is what we refer to as bin norm, binary normalization layer. And we define this as an optimization problem. And once this is solved, we end up with this, which is pretty much an adaptive sigmoid operation, which ensures that our descriptors sum up to a certain number of size, in this case, k, which is set to, for example, 64. Now, while this is an optimization problem that we need to solve during a training process, it can very easily be replaced by a top K operation during inference. What does this allow us to do is then when we're trying to match two images, we can get comparable performance to, for example, superpoint while being an order of magnitude faster. But for slightly more detailed results, we are able to match two images an order of magnitude faster to superpoint, at the same time have a 3D map, which is significantly smaller in size. Due to the quantization strategy, we are able to, the network quantization strategy, we're able to also get the descriptors much faster. And therefore, since matching is faster and inference is faster, then naturally the whole localization step is faster. So these are the results on the Aachen day-night data set, a very common benchmark for this kind of networks. But then we also asked whether we can also improve in new and more challenging scenarios, such as the map-free visual relocalization. I don't think there's much point in talking about much this one, exactly about this benchmark, because Eric talked for quite a bit of time about this. But the key finding here is that once again, when compared to other learned alternatives such as superpoint, we again achieve comparable performance, but significantly faster in the two different metrics that Eric was talking about earlier. So to conclude, in this work, we wanted to sort of bring up the point that while of course most works focus on making these work much better, And there's, of course, a lot of merit into this. We should not forget about speed, because at the end of the day, we want to use these networks in real time, in practice, and not just have them in huge clusters that are only for academic purposes. We presented the layer partitioning and traversal strategy for the structured quantization of the network. We proposed the use of binom to generate binary descriptors. And both of these allowed us to be an order of magnitude faster than other learning alternatives. So we kind of see this as a first step towards bringing this closer to mobile deployment. But are we done? No, of course not. So here I'm talking about some future directions. First and foremost is, we used binom in this scenario for binary interest point detection. But of course, there's other applications that can benefit from this, for example, image retrieval. And of course, while this is an interesting component, it's still a module that can be used as part of larger pipelines. And it will be interesting to see how it can help improve robotic and augmented reality pipelines, whether new or existing ones. So thank you all for your attention, and I'm happy to take any questions if you want to go easy on me.
I think I have like one super stupid practical question. How did you like implement this binary stuff finally? Like you don't have like any framework to do this, right?
Yeah, that's a great question. And that's something that, okay, so I guess a slight disclaimer on this scenario. So often quantization depends very, very heavily on the hardware and the infrastructure behind to support this. So for example, some mobile devices and the accelerated chips that have on them may support only floating point 16, maybe in date, some go a bit lower. For this one, we used LARC, which is a compute engine that runs on CPU, and it allows to achieve performance improvements even when using binary networks. This is not always the case, but I think the more we start trying to shift these networks to on the edge, there's going to be more and more of a need to actually develop these frameworks, and as an extent can benefit more from these kind of speedups.
Thank you.
Thanks.
Yeah, thanks again.
Okay, so I'm sorry. It turns out the MacBook uploads and deletes, but okay, here we go.
Second talk is what we need for.
Can I shift this? So you can do this, or you have mouse. Okay.
Yeah. Yes. Okay. So hello everyone. I am Gabriele, and I will present our paper about the application of local feature for cross-domain visual place recognition. Firstly, what is visual place recognition? It's not shifting the slide.
Shifting.
Yeah, changing slide.
Yeah, it does. It's okay. Maybe there's some problem with connection. Okay. I guess it's because you have also PowerPoint. And here it shifts.
Ah, there you go.
Yeah. Okay. So what is visual place recognition? Well, quite simply, given a query image, we want to estimate its geographical position within a known area of interest, usually around the city. So in our paper, we do a benchmark of re-ranking methods, and this is our adopted pipeline. The first step is fixed for all methods, and we just use the state-of-the-art for global descriptors, which is cosplace, to obtain a short list of candidates for each query. And keeping this part fixed enables us to achieve a fair comparison between all the methods. And then we test different kinds of re-ranking methods, whose goal is to basically assign a score to each candidate and re-rank them, trying to improve the precision of the retrieval. Now, there exists some methods specifically designed for re-ranking in retrieval tasks, but there, as you know very well, there are also methods for image matching, which to my knowledge have never been tested for VPR. So this is how we use them. These methods detect and describe some local key points in the images, and then there is a matching step, which can be done either via ransack or some learned matcher. And then for ranking, we simply use the count of matches as a score. So coming to our contributions, we have witnessed a growing number of papers for ranking retrieval, and in parallel, we've seen the same thing for image matching methods. But within this context, we see two issues. Firstly, re-ranking methods are usually compared within different setups, so different backbones for retrieval or even different methods. And we argue that to achieve a fair comparison, they should be evaluated under the same conditions. And on the other hand, for image matching methods, there is often a lack of some downstream task on which to evaluate these methods. And so our benchmark provides a solution to these two issues. But we did not just benchmark re-ranking methods for VPR, and there is one additional point. So it is well known that one of the common failure cases for global descriptors is when they encounter heavy domain shifts, such as night images or heavy viewpoint shifts. And so we note that local features are inherently more robust to these conditions. And so our question is whether we can close this domain gap in VPR by relying on local features. Although we know that existing datasets have some problems that don't allow us to study this issue. For example, Tokyo 24/7 or SVOX, they only have a small scale database, which is not realistic for a practical application that wants to localize within an entire city. And for SFXL, there is not a set of queries with a clear domain shift that can allow to highlight these effects. And furthermore, we've seen a saturation of performances on this data set. So on our benchmark, we achieve almost 100 points of recall on Tokyo. And so this means that existing data sets simply cannot keep up with the new methods. So we deem it necessary to create some new ones. And so we manually collect and label 2 new query sets from Flickr for night and occlusion conditions, and we can use them to match images against the database of SFXL. These are some examples from the night dataset, and as you can see, the night domain is not the only challenge here, and also for the occlusion dataset. So now we can go on and see some results. Firstly, we can note how on the SFXL test set, which is quite challenging for retrieval-only methods. And despite this, we see that with these re-ranking methods, we can almost saturate performances on it. On the other hand, on our newly proposed data sets, performances are much lower and there is still a long way to go. And despite all these methods are able to improve on the retrieval baseline, we see that there is still quite some room for improvement on these data sets. And we also note that these data sets are so challenging that even increasing the number of candidates does not bring much improvement. And this is important to keep in mind if you're designing an application, because these methods have a high cost that's proportional to K. Another thing is that usually in VPR, there is a threshold of 25 meters to deem whether a match is correct or not. And on existing datasets, this does not matter very much. But on our new datasets, which are more challenging, we see that if you increase the threshold, for example, to 100 meters, this is quite an impactful choice. And so if you're building an application, you should carefully consider this aspect if you can accept higher errors. These are just some qualitatives to show how some of these methods work very well. For example, CVNet that uses a hide-and-seek protocol during training, and it is then able to work very well even with heavy occlusions. One more interesting result is that, for example, if you look at these recalls on Tokyo, so on Tokyo, each daytime images has its counterparts with the same pose taken during the night. And we see that basically this is not a problem for any of these methods, and they can recognize the image regardless of the night or day. And so this brings us to the conclusion that night itself is not really the challenge, but when it is combined with heavy viewpoint shifts or artificial lights or things that you saw in the examples from our data set. And that's what makes it real challenging. So in the end, local features are actually robust to the domain shift itself. And so concluding, our main contributions are the creation of these new query sets that can hopefully foster future research. And together with these data sets, we release a processed version of SFXL, since the whole database is quite big. And so we release only the top 100 candidates for each query with different retrieval methods, so that it can be easier to use this data set together with our open source software. And hopefully this can make it easier to benchmark re-ranking methods and also provide a downstream evaluation for image matching methods. So that was all from me. And if you have any question, I'm happy to answer.
If there's no question, I have a question. Do you have like poses and how accurate are they for like your introduced new ones?
Okay, no, we do not have the poses for them because they were collected from Flickr. So what we did was checking that there were night images. So we had some network to classify whether it was night or day, and if it was an outdoor image. And then since Flickr labels are quite noisy, we had some scripts to check them manually and verify the coordinates. And the same thing goes for the occlusion dataset. So we use some bounding box to select them. And so, yeah, they are specifically designed for VPR, so we're not able to obtain the pose.
Thank you.
Okay.
So it's like astronaut detection. Okay. The opening is in progress.
Okay.
Yes. Okay. Okay, what I will try to do in the meantime is okay. So is it almost done? Sorry for this. Okay. Here we go.
All right. Hello, everyone. My name is Alex Doken, and I'll be presenting Find My Astronaut Photo, a project by myself and Ken Fisher out of NASA's Earth Science and Remote Sensing Unit at Johnson Space Center in Houston, Texas. We'll begin by discussing what astronaut photography is, talk about the barriers to geolocalizing this imagery, present the Find My Astronaut Photo framework, our method for geolocalization, and then discuss the key aspect of this method, finding a discriminative matcher. We'll introduce the AIMS dataset, which we'll use to evaluate various matchers and show the results on this dataset. We'll start with a brief history of astronaut photography. Astronauts have been taking pictures of Earth from space for over 60 years, and whether you know it or not, you've probably seen some of these images, like this famous one from Apollo 8, the Earthrise image. Although you've potentially seen it more like this, where it's been rotated and enhanced. Collecting and managing this imagery is the duty of my group. And this imagery is primarily used for research, disaster response, and public engagement. We haven't been to the moon in a while, so today most astronaut photography comes from the International Space Station, which is an orbiting lab 400 kilometers above the Earth's surface. It rotates around the Earth 16 times a day, so that's 16 sunrises and 16 sunsets, and it has various observation platforms like this cupola window, from which astronauts can take these handheld digital cameras and take pictures of the Earth. To date, we have a 4 million photo collection, and it increases by about 100,000 photos every month. Astronauts are always up there taking photos. Unfortunately, 90% of this imagery is missing critical geolocation information. We don't know what's actually in the photo that they take. And the 10% that does have that information was painstakingly added by hand. And so you may ask, with other remote sensing platforms like satellite imagers and Landsat, we know exactly what's in an image. So why do we not know the same thing for astronaut photography? And that's due to the different acquisition conditions. So for both of these situations, we know the spacecraft position and attitude. We know where the ISS is all the time. But unlike for satellite images, where we know exactly where the camera sensor is pointing, this time we have a human in the loop that can take this camera, point it out of any of these windows, and see a variety of locations on the Earth. So now let's put ourselves in the perspective of an astronaut and see what they can see. So here we are looking through the cupola on the ISS, and we can see 2,500 kilometers away in every single direction. And with the variety of focal length lenses available to add to the cameras, the crew can take really high quality imagery really far away. So we have from 50 millimeters all the way to 1,150 millimeter focal lengths. And so let's go through the viewfinder now and find our image. And so this looks pretty good. Let's snap a photo. And so now let's answer the question, how on Earth do we find where on Earth this photo is? And all we have to go off of is the photo itself and the image metadata, the timestamp and the focal length. And so from that timestamp, we can figure out where the International Space Station is and what part of the Earth is visible at that point in time. So that's that white line here. The next thing we have to do is discretize this space into patches based on the camera focal length. So a camera with a 400 millimeter focal length will have a smaller ground field of view. It'll be more zoomed in, one might say. And so we have more patches to take up the visible Earth area, but each patch covers less area. With 100 millimeter focal length, we have these large expansive patches that cover the visible Earth area. Then we can generate a satellite reference image with the extent of the patch for each photo. This is because those satellite images are georeferenced by nature. So we know exactly what that area of the ground that's encompassed in each patch looks like and can just quickly pull a satellite image for that area. We'll then use an image matching method to determine if our astronaut photo in orange here and an image patch from satellite represents the same location, putting it through our matcher. If it meets our matching criteria, that's great. We'll continue on with fine localization like Ransack. Otherwise, it's not a good match. We'll go ahead and we'll try another satellite reference image. And so the answer to the question of how on Earth do we find where on Earth is this, the Find My Astronaut Photo pipeline, which looks very similar to a traditional visual localization pipeline, but I want to highlight a key difference here in the blue box. We do not have a static database of images here. And so we do have some sense that it's more likely that the astronauts take photos of the Earth that are closer to where the ISS is rather than far away. And so we order the patches of satellite reference images by this distance. And so we'll first visit this darker blue region here, and then the lighter blue and the lighter blue spiraling outward and testing these various images. And we're doing this ad hoc in an online manner. And so as with all of these visual localization pipelines, the key aspect is the matcher and the strength of the matcher. And so let's discuss a few things that make astronaut photography a difficult challenge for these matchers. And the first is that finding a best match would require checking each patch. There can be 1,000+ patches for high focal length imagery, and checking just one, especially if we use a local feature-based method, is pretty expensive. So we're actually in search of a type of matcher that's discriminative. So if, as we see here on the right side, we find a patch really close that has a really good matching score, we're good. It's a good match. We don't need to actually find the best match because we know that our matcher is discriminative such that a good match is always the best match. Second, many areas on Earth appear similar or have little texture to go off of. And this is made even worse by a requirement that we need to minimize false positives in this kind of early stopping setting when we're not searching the entire visible area and we want to stop early. If we have a false positive, that would be wrong information that's entered into our database, and the image will not be available to researchers in the right location on Earth. So we really want to make sure that we reduce those false positives. So it's okay if we find a good match early, or if we find a bunch of bad matches and finally a good one. But in this final scenario, if we get a positive matching criteria answer in item number 1, we'll never actually go forward to visit that fourth patch, which is the true correct patch. Each astronaut photo has a unique set of patches that varies in scale and location. Here you see one in the Vancouver area, as well as in Africa, and these have the different focal lengths as well. And so we don't have a pre-computable database. We can't store features or even store the patches. And so we would like to do this quickly. And so some scale robustness will allow for more leniency in patch generation. If we can generate patches that are a broader scale, there are fewer patches to fill up that visible Earth area. Next, we will always have an incomplete overlap with astronaut photography. This is co-visibility, not occlusion, apologies. And that's because of our discretization of this truly continuous space where the astronauts could take pictures in. Finally, we have a few things that are familiar in many image matching settings. We have variable illumination conditions. We have nadir straight down or some obliquity, some affine transformation of the imagery. And then one interesting note is that astronaut photography has no canonical orientation. When a crew member is sitting there with a camera, north is not always up and there's no sense of true direction in space. So we need to be robust to rotation, illumination, occlusion, and viewing angles. So to analyze different matchers in this setting, we present the astronaut image matching subset, 323 astronaut photographs that have already been localized by human experts. It has variation across various things that we discussed beforehand. And we present the astronaut photos, patch definitions, the true correct patches, and satellite reference images. These will be released on our website here. And so the input to this pipeline is an astronaut photo and all of the satellite images. You need to present the best matching satellite reference image. We score this on precision and recall. We can use this evaluation. We can use the AIM set to evaluate various matchers. And so we compare both embedding-based or global descriptor matchers using L2 distance, as well as detector-based and detector-free matches. We first try to find the optimal matching criteria for each detector on our data sets. This is kind of a very practical thing that we want to do to optimize for our own data set. And then we can compare each model to the other models using this optimal criteria. And that looks a little bit like this. So the annotations on this plot are, in the case of local feature matchers, the number of inliers that we use for determining whether a match is correct, our inlier threshold. And the first thing you'll note is that all of the embedding or global descriptor-based matchers are not discriminate enough in a broad sense. So there's no distinct L2 distance measure that we can say will accurately differentiate between good matches and bad matches. If we do use a top N approach and we do that whole search space, we do get good results. But this here shows when we're trying to find a uniform distance so we don't have to search through every satellite patch. You'll notice that detector-based and detector-free matches, this is inlier correspondences, and we are able to find pretty strong and accurate matching criteria here. So using our best matching criteria, we can see how our results are on the AIM set, and we have a few interesting items of note here as well. First, detector-based matchers like Superpoint Superglue and D2Net are the most robust to scale changes. So by scale change, I mean if an astronaut photo has 5 meters per pixel, we can actually use a detector-based matcher that has 10 meters per pixel and still get a strong match. This is not true in some of the detector-free or lofter style matchers. Next, Matchformer is most robust to occlusion. We have a separate model that estimates the cloud cover in an astronaut photo. And so in those high cloud astronaut photos, we see that Matchformer actually does best. Finally, SE2 Lofter, presented at this conference a year ago, is the most robust to rotation, unsurprisingly, as it's trained for this. And all the other matchers are shockingly poor for large rotations. So we have the AIM set divided into north-facing, east-facing, west-facing, et cetera, and a relatively even split across these different directionalities. And in all non-north-facing, and all satellite imagery is north-facing, in all non-north-facing scenarios, the other matchers fail completely. And so due to this property itself, we choose SE2 Lofter to power the Find My Astronaut photo pipeline. We've used this pipeline to find 57,000 images. So obviously we have 4 million, so we have quite a ways to go. And we'll be continuing to run this pipeline and explore additional matchers for higher precision and recall, as well as other matching methods. Perhaps there is some global descriptor faster method that we can use. We'll be doing some engineering improvements to improve the per photo speed. This is just so we can burn through that backlog of 4 million photos. And we'll add support for nighttime photography. We have a sense that this will work for nighttime photos, but it's not often used in that case. Here we have an astronaut photo itself, fully georeferenced. This is the Washington, D.C. area. And to emphasize, we had no idea where on the Earth this was when it was taken. The actual ISS was somewhere over the Carolinas when this photo was taken. So pretty far from DC. And finally, thank you to the image matching workshop organizers, the reviewers, and you all, the image matching community. We use your matchers in this application. So we really appreciate all of the hard work that you've put into creating these. Thank you very much.
Sorry, this question in chat. So what is the per photo speed of like finding where it is?
Currently, we have an average speed of under a minute per photo, but this can balloon up to 5 minutes and it's heavily dependent actually on whether you are searching the whole space here. And if you find a good match quickly, it can take under a minute. If you have to search this entire space, 2,500 patches, it can take about 5 minutes to get through that entire space. So we really prioritize the discriminativeness of making good the best as well, so that we can go quickly.
Any other questions?
Do you see the domain shift between the queries that are taken from the astronauts to the database and used for geolocation?
That's a great question. In general, we do. There's different satellite imagery types like top of atmosphere and surface reflectance. We actually pre-process or post-process the satellite imagery to add in some sort of atmospheric haze and occlusion or some kind of synthetic version of that so that they do appear more similar. Otherwise, they would have slight color shifts.
Thank you again.
Next speaker would be via Zoom, and I would be the slide monkey. So, where who is the speaker? Can you ask who I should unmute?
Cristiano. That person.
Ask to unmute.
Okay, yes.
Hello?
Hello.
Can you say something?
Yes. Can you hear me?
We don't weird. Audio is
audio is not here. Okay.
What happened? No, I think it's our audio that's
So what should we do?
Edward, can you try talking? Yeah, it is weird.
We don't share Zoom through Zoom. Sorry, that's speaker. Okay, so
Yeah. So we did test the audio output just before, and it seems it's not.
Okay, Cristiano, you're now the host. Try to say something now. Maybe it would work.
Can you hear me now?
No, I think we lost the audio.
Okay, we lost the audio. Amazing.
Okay.
Let me try to.
Then we are doomed if it's true. Okay.
There's always something. Let me.
I don't know.
Yeah, can you try where's the Scarlet Solo? Yeah.
Say something now.
Hello. Does it work now?
Yeah, somebody's still. I think it's. Oh wait.
No, it doesn't work like this.
Okay, so the speaker, let's then turn it into external headphones. Yeah, I found it.
Where?
External headphones.
No?
Yeah, we can hear, I think. Can you try talking?
Hello?
Yeah.
Amazing.
Okay. Now it works.
Yes.
Great.
Wow.
Okay. So should I share my screen with the slides, or I think that
actually share? I think it no. Oh, sorry, we forgot to share it Zoom.
one moment. Does it work now?
And I can see it. Do I have control over it, or
You say next, and I click.
Okay, this is gonna be fun. So I guess I may start, right?
Yeah, you can start.
Okay, so hello everybody, my name is Cristiano, and in this talk I'm going to present to you our spherical key point matcher named SphereGlue. Next. Let me start by introducing how we compute the key points first. So instead of computing them directly on the panoramic images, we actually compute a tessellation on the sphere, and using the resulting local planar approximations that we named shard images here, we compute the key points on these shard images, and then we map them back onto the sphere. Now, with this approach, we can compute virtually any key points we wish, but in this paper we focused on two handcrafted and two learned approaches for the sake of comparison. Next. So how to match these key points now? So in the context of spherical images, if you look out there, you probably find the nearest neighbor search with its two famous flavors, the mutual test or the cross-check and the ratio test. Now, with the first one, you will probably get lots of matches, but they tend to be noisy. And with the second one, the matches are usually clean, but they tend to be insufficient. So the first question we have here is, can we learn a better way to do it? Next. So of course, when you look at the literature, we stumble into the SuperGlue paper, which is an excellent work. And among its many interesting aspects, here I'm going to focus on two of them, the self-attention and cross-attention layers. So while the self-attention deals with the relationships between key points within the same image, the cross-attention layers, they look at the relationships between key point in one image and key points on the other image. Now, when applied to spherical images, SuperGlue does actually a pretty decent job, but as shown here with the red rectangles, in this case, it completely missed an entire wall of the scene. So there is room for improvement. Next. Now, again, please consider the spherical images. So this idea of the self-attention, of attending to many, many key points within the same image, seems a bit of an overkill in the case of spherical images, because consider, for instance, the antipodal key points. Is it really necessary to attend to key points that are on the other side of the sphere, like points or key points that are far away? So, well, probably not. Then the other aspect is a more practical one. So when dealing with high resolution spherical images, the number of key points is also very high. So this idea of the self-attention, of attending to many, many key points within the same image, kind of have a performance issue. So in other words, it doesn't scale very well for high resolution spherical images, which leads to the next question. Can we, by design, improve on this? Next. So the first thing we did was, instead of using pixel coordinates for the position encoding, we switched to unit Cartesian rays. This way, we can compute the neighborhood on the sphere in a much more natural and an efficient way. The second thing was to use a spherical graph to represent the key points. It's like a net stretched over the sphere, right? And then we replaced the SuperGlue self-attention mechanism with Chebyshev convolutions. So Chebyshev polynomials, they fit very well to this idea of localized filters. Plus, they are very efficient to compute. Next. So here's an overview of the whole architecture. After computing key points, as I mentioned, we use Cartesian rays, unit Cartesian rays, for the position encoding, followed by the Chebyshev convolutions. The resulting embeddings are then fed into cross-attention layers, and in contrast to superglue, which uses alternating self and cross attention layers, here we only have cross attention layers. The rest of the architecture is just like superglue. We have the score matrix with the dustbins followed by sinc horn, which yields the partial assignment matrix. Next. So since this is a self-supervised learned approach, we need the RGB images to compute the key points, but we also need the depth maps and the relative pose between the cameras so that we can compute the ground truth key point correspondences to train the network, which we do on a single RTX A6000 over 60 epochs. And we use only 10 scenes, out of which we use 15,000 image pairs with key points detected on 25 megapixels images. Next. So the first three columns of this figure I showed you before, right? So I added the fourth one with our results for a visual comparison. So as you can see here, sphere glue can compute or can find almost as many correspondences as the mutual test, but with significantly less outliers. And it's consistently finding more correspondences than the ratio test. Next. So also for visual comparison, I put here side by side the superglue that I showed before with the sphere glue results. So as you can see in this wall that was missed by superglue, sphere glue can easily find the correspondences. But these are, of course, just qualitative results. What about quantitative results? Thank you. Among other things, we compute the area under the curve for the true view pose error at 5, 10, 20 degrees, just like other papers do, including superglue, right? And I know there are many numbers here, but please focus on this blue rectangle. This first scene is the case where our approach did not outperform the baseline, which is the nearest neighbor approaches. But in other scenes, it considerably outperforms everything else. Now, if you look at this small green rectangle on the other side for the last scene, you see that even though superpoint dominates the other results, for this case, SIFT and KP2D perform better. So for some reason, superpoint performed poorly on this scene, and this is probably the reason why the superglue also performed so bad in this case, as shown in red up there. It is even worse than the baseline approaches. Next one. So as limitation, we can mention the scalability of the cross-attention layers, because this is still very dependent on the number of key points. For the same reason, the number of key points, the score matrix tends to be quite large. So this causes memory issues. It may not fit the GPU memory. So at the moment, we limit the number of key points to 20,000 per image. So as future work, of course, we plan to address those limitations, but also add more key point detectors, train on a larger data set. We are actually working on that, and perhaps extend it to high resolution perspective images as well. Code can be found on this link. This is my email contact. And next slide. Thank you very much for your attention. These are some extra results in case someone wants to ask about other measurements, this matches score precision recall.
Thank you. Any questions? Okay, so the question is, how did you obtain like key point, like pixel level key points there, provision?
Can you repeat it, please? I didn't get it.
How did you obtain pixel level supervision for training the sphere glue?
We use first, we don't use like pixel level, we extract the key points and map them onto the sphere. So we have points distributed all over the sphere, and we use the depth maps. So we back project the ray through the image, and if you go a few more slides back, like one more slide back, yeah, slide number 8. there. So we have the depth map for every single image. So we back project array through the key point location and then sample the depth map at that location. Then we have a 3D point. And we project that 3D point onto the other image because we know the relative camera pose. These images are rendered with Blender, for example. And then we have the correspondence. Of course, we need to do some checks for occlusion and everything, which we do, but we can establish the correspondences in this way. So it's a simple geometric relationship. I hope this answers the question.
Yeah, thank you. Okay, now next speaker is you present on Zoom? Okay, it seems that there is no speaker, so we'll present a video instead. Okay, wait, now we need to
go to system settings.
Okay.
Go here.
Yes.
And sound. And then you have select the output as headphone. Yeah, that should
External. Okay.
Of China, we presented SEM, structured epipolar matcher for local feature matching. Image local feature matching serves as a fundamental task in many 3D vision tasks, such as visual localization, SLAM and structure for motion. By studying the previous matching methods, we sum up two issues that are imperative for obtaining the dense correspondence between images. First is the limitation of appearance feature. As human beings, when we search for correspondences between a pair of images, we do not just compare pixels. Instead, we first look for conspicuous and easily matched anchor points in the images. By utilizing the relative positional relationships between pixels and anchor points, human beings can easily overcome the challenges posed by textureless and repetitive texture areas. This process is also inspiring for learning-based approaches. Existing methods only focus on extracting features from appearance, which is not distinguishable enough. See the figure. Some points with rich texture can be easily matched correctly with appearance feature. We call them anchor points, which marked as red in the figure, but some points with poor texture, such as A, B, and C, are quite similar in appearance feature, which is one of main challenges to appearance-based methods. We observed that structured feature is ignored by these methods. If relative position of A, B, C to anchor points is considered, it can help to find correct matching. Another problem is irrelevant regions. Existed mainstream methods usually apply all pixel to all pixel attention and matching process, so the accuracy is influenced by irrelevant regions. See the figure. D, N, E is correct correspondence, but F is also similar with D. If global attention and matching are applied, a wrong correspondence between D and F may be deduced. We find that geometric prior is ignored in most previous methods. In particular, epipolar constraint is helpful in matching. See the figure. Epipolar lines are marked as red. According to them, correct correspondence of D must rely on blue region. Here we broaden the epipolar line to a region for error tolerance. As a result, another similar point F is filtered and doesn't take in attention and matching with D, which increases the To address the aforementioned two problems, we propose structured epipolar matcher for local feature matching. We propose a unified course to find iterative architecture named structured epipolar matcher, taking structured feature and geometric prior into consideration. The figure shows the whole architecture of our proposed method. It contains an iterative epipolar course matching module and two submodules. First, the initial course appearance features are extracted by a CNN backbone. Then the features are iteratively updated in an iterative epipolar course matching module, which is the course stage. In each iteration, structured features are fused by structured feature extractor module, and then attention and matching are applied with epipolar constraint to update the matching matrix. The camera relative position, RT, is obtained by ransack algorithm. After the course stage, a refined matching module conduct a fine stage. Our first novelty is structured feature extractor, which extracts structured feature and fuse it into appearance feature. First, we select some high confidence correspondences as anchor points. marked as red in the figure. For each point, Q, in the image, we calculate the coordinate differences and Euclidean distances from Q to all anchor points. Then, structured feature is obtained by concatenation of normalized coordinate differences and Euclidean distances. Here, we apply L1 normalization for scaling invariance, and use normalized Euclidean distances to enhance rotational invariance. After that, we fuse structured feature with appearance feature by concatenation and MLP later. In this module, relative positional information with reference to anchor points is encoded into output. Our second novelty is epipolar attention and matching, which takes epipolar constraint into attention and matching process. The attention and matching are conducted in an iterative manner. First, we obtain relative position, R, T, from previous matching matrix, M, by ransack algorithm. Then epipolar lines such as P0 and 0, P1 and 1, can be calculated from relative position by epipolar geometry. Here, we broaden epipolar lines to regions with the set width for error tolerance, marked as green, because relative position is not accurate in iterative process. Correct matching point may not lay on the line. After that, attention and matching are applied between P0 and corresponding epipolar region. Features and matching matrix are updated. In this module, irrelevant areas are filtered in attention and matching process by utilizing. We conducted extensive experimental to evaluate our proposed method. 4 challenging benchmarks are evaluated, including homography estimation in H patches, relative pose estimation in megadepth and ScanNet, visual localization in InLog. We obtained new SOTA performance in all of 5 benchmarks, demonstrating the effectiveness of our proposed method. The ablation study also proves the effectiveness of each module. These are some visualization results. The left is the points and corresponding epipolar banded areas in source images, and the right is qualitative comparison between match former and our proposed method. To sum up, we propose SEM, a novel structured epipolar matcher for local feature matching. It contains 2 novel modules, a structured feature extractor, generating and fusing structured feature to complement the appearance features, an epipolar attention and matching module, utilizing epipolar constraint to filter out irrelevant matching regions as much as possible. We obtained SOTA performance in extensive experiment. Thanks everyone.
Okay, amazing. Okay, next speech is also video, but the author should be there on Zoom and able to answer your questions. And hopefully it's not text to speech.
Hi, I am Amok Tiwari, and I will be presenting our work Convolute, Continuous Volumetric Embedding for Human-Centric Depth Correspondence Estimation. This work was done along with my colleagues Pranav, Nakul, Astit, under our guide, Dr. Avinash Sharma. All of us are associated with the Center for Visual Information Technology at IIIT Hyderabad, India. Our objective is to establish correspondences across images of humans, where the images may have different subjects present in different poses. Our motivation for this work comes from its possible application in virtual try-on and 3D human design. This problem is challenging as humans exhibit large variations in shapes and poses as shown here. Further, modeling clothing details, especially loose clothing like these, poses an additional challenge. Our 2015 work called FMPL presented a parametric human body model where we can model different human shapes and poses based on the parameters too. Our 2018 work called DensePose learn to establish dense correspondences between images and the SMPL model. Our follow-up work to DensePose called CSE also tries to do the same task, but by learning a common embedding space for images and the SMPL body model. However, all of these methods only establish correspondences between images and the SMPL body model. They do not model clothing details, something which we want to do. Our 2022 work called Body Map attempts to model clothing details. It does so by deforming the SMPL to match the closest 3D human scan. However, this process is not perfect because there are limits to how much the SMPL can be deformed. For example, for images of loose clothing like these, you can deform the SMPL slightly away from the left, but there will still be some space left between the limbs. We aim to resolve this issue in our work by proposing a new representation which can handle points arbitrarily far away from the parametric body model. To do so, we first define some anchor points at some key chosen locations on the parametric body model and initialize them with significantly distinct embeddings. Then we geodesically extrapolate to compute embedding for the remaining points in the body model. Next, we register the SMPL to match the pose of the 3D human scan. Finally, we calculate embeddings for the 3D human scan based on volumetric extrapolation from the K nearest SMPL value. Our key novelty lies in the fact that the above process allows us to model points arbitrarily far away from the SMPL body model. For training, we render the RGB images and corresponding Convolli embedding from different viewpoints and train a unit-size encoder-decoder network to predict Convolli embeddings from images. Similar to body map, we also make use of CSE predictions as a prior to our network. For inference, we simply give the RGB images and their corresponding CSE predictions to the network, which then outputs the per pixel Convolli embeddings. Finally, to establish correspondences, we just do a nearest neighbor search in the embedding space. For evaluation, we make use of geodesic distance error, where for each pixel we compute its corresponding ground truth and predicted 3D vertex based on the ground truth and predicted Convolli embedding. And then we compute the percentage of pixels with geodesic distance less than a threshold. GDE helps us to estimate the accuracy of correspondences between images and 3D scans. Further, to evaluate the richness of a representation, we propose a new metric called neighborhood consistency score, where we impose ordinality constraint on the representation. That is, geodesically nearby vertices should map nearby in the embedding space, and faraway vertices should map far away in the embedding space. We evaluate our method on 3D human and T-human datasets, both of which contain varied humans in varied poses and clothing. We are able to outperform body map on both GDE and NCS metrics on both the datasets. Further, we can see an evaluation study on the choice of different priors and also an evaluation study on the choice of anchor points. Here, we can see that for randomly chosen points, increasing the number of anchor points helps. This is because more anchor points would lead to the representation having more unique values for more unique embeddings. However, our manually chosen anchor points still give better results than even 100 randomly chosen points because the anchor point, the locations we chose for the anchor points correspond to some key body locations like the shoulder joint, head joint, and torso. Here we can see a qualitative comparison with body map. And these are some additional results of our method on some challenging cases. In summary, we introduced a novel dense surface level representation and also learned to estimate the representation in the MS space for dense human correspondence matching. Our key novelty is that we can handle points far away from the parametric body model. Additionally, we also introduced a new metric called neighborhood consistency score to evaluate the richness of a representation. Follow-up works to this work should explore explicit temporal and multi-view consistency, use of higher dimensional embeddings, and also using better architectures for learning in the image space. Thank you.
Okay, thank you. Any questions here? I don't see anything on Zoom.
Okay, if there are no questions, we thank you again. And we go to next speaker, which would be presented in a similar way. With live QA if there would be any questions. So let's go.
Hello, my name is Jong Lee, one of the author of the paper titled Multi-Scale Concurrency Sequence Descriptor, presented at the International Workshop in CVPR 2023. Today, I will explain our proposed method for sequence descriptor. Let's begin by considering the resolution of the feature map from which we obtain the descriptor. Assume that we have the same number of layers and channels for generating the feature map, and the key points of system are represented as stars, and figures are with small squares. In the left figure, each key point has its own feature vector, which is not shared by others. However, these are positioned in terms of computation and memory cost, which increases with higher resolution. On the other hand, the right figure shows a feature map with lower resolution. With fewer feature vectors available, descriptors can better distinguish key points that are far apart. However, it becomes difficult to distinguish nearby key points if they are likely to share the same feature vector at the same pixel. To address this trade-off, we developed a multi-scale local descriptor with a technique called negative sampling, which I will explain in more detail later. Another motivation behind our work stems from the limitations of binomial interpolation, which is commonly used in previous key point descriptors. As you see in the equation, binomial interpolation only focuses on the ratio of surrounding feature vectors, but fails to adequately capture positional information and the non-linearity of local descriptors on continuous domain coordinates. So, from this, we introduced a module called LIKD, local implicit key point descriptor, to address these issues. The overall picture primarily consists of convolution layers with mask plane, and the location and score head equals the key point coordinates and their scores. We followed the architecture from type P to D of previous subtype key point decision model. From the detected key point coordinates, we apply our LIKD module to obtain descriptors from two different resolutions of the feature map. So LIKD is designed to aggregate the feature vectors surrounding the key point in a local region. Unlike binomial interpolation, where the weight of each feature vector is determined by the ratio of corresponding area, our approach employs long parameters to take into account both the feature vector and its coordinates. To accomplish this, we utilize a small NP with value activation function and leverage the relative coordinates as inputs. By doing so, we are able to incorporate the position information of the key points with the feature map. The other advantage for our approach is that it allows for the description of useful descriptors by weighting specific feature vectors regardless of its relative position within the surrounding sphere region. During training, conventional physics consider areas near the true corresponding key points as positive, indicated by blue region. The remaining red areas represent negative region, whose descriptors should have a larger distance compared to those in the blue region. The diameter of the blue region represents the state radius. In our approach, we will adjust the state radius and positive area based on the resolution of the feature map explained in the architecture. The adjusted positive and negative areas are then used for sampling the descriptor to calculate the loss function, such as triple materials. For the 16 times down sampled force feature map, we sampled negative descriptors from order region compared to the conventional setting. On the other hand, for the 4 times down sampled fine feature map, we sampled negative descriptors only from some of nearby areas. The purpose of this separate sampling strategy is to take advantage of the characteristics of feature map. We designed the loss function to enable the coarse feature map to distinguish descriptors located far away from the positive one, while the fine feature map focuses on distinguishing nearby descriptors. As a result, each descriptor specializes in its specific purpose. The key point scores as targeted by KP2D aim to achieve repeatability. It means that high scores are assigned to key points that are likely to be located in the same location, irrespective of changes in color or viewpoint. However, the previous colored term do not reflect how much the key point is likely to be truly matched. So we introduced a new term called relative reliable score to assign high scores to points that are likely to be correctly matched. We utilize the metric for correct matching based on the two-plane modulus, incorporating descriptors similar to it in the both terms. Consequently, the loss is minimized when the score is high and the similarity between descriptors in the positive pair exceeds that of the negative pair. This indicates that the stated key points are likely to be true matches. To summarize the loss function, our model is trained using multiple loss functions. We utilize the location loss and score loss from KP2D for key point prediction. For descriptor training, we employ separate loss functions for each feature map, one for the first feature map and the other for the final feature map. When training with the 12-parameter loss, we apply negative sampling that varies depending on the resolution of the feature map. Since we concatenate the descriptors during inference time, we also employ concatenated descriptors for training during the third loss. To train our model, we use two datasets. One is the COCO 2017 dataset, which will no longer pay for pre-training our networks. After that, we trained our model using US3D dataset with non-relative pose and depth. Our evaluation results for image matching are presented in the figure. The graph illustrates the mean matching accuracy on the age-fit dataset, and our method is represented with solid red line, which consistently achieves the highest accuracy compared to the other approaches. To further highlight the support of our performance, we provide a comprehensive comparison with state-of-the-art methods in the following table. We also conducted evaluation on both the scannet and negative datasets with different thresholds for relative pose estimation. Taking into account that pose space, and caps were trained on the negative, our method demonstrates comparable performance and even outperforms them the scanner dataset, indicating the disparity generalization ability. For localization tests, we evaluated our method on the IN dataset, including both versions 1 and 1.1. The results demonstrate that our descriptor achieved competitive performance compared to the other methods. Moreover, there is a potential for further performance improvement when combined with our descriptor with other state-of-the-art key methods. In summary, we have proposed a multi-scale approach for key point descriptor generation, where key points are positioned continuously across the image. Additionally, by training each descriptor to enhance their individual performance, we have devised negative sampling strategy that considers scale awareness and complementarity. As a result, improved discrimination ability of our proposed descriptor enables it to outperform previous methods across multiple evaluation scenarios. Thank you for your attention.
Yeah, thank you. Any questions? If there is no questions, we go next. Could you please help with sound possible?
So let's try to reshare. Okay, that's fine. Yeah.
Okay. And should we change the
system?
System, yes.
I think it should be okay. So yeah, external here. No, actually, input is set to should be set to the
But let's import, that's not the thing.
Yeah, so I'm gonna try to see if this works.
Ah.
It's not gonna be ideal, but still something better than nothing.
According to their similarity score to the query. Extracting and merging system feature both spatially and temporally plays a critical role. Some work resulted issued by a multi-stream architecture, where each stream can fill a particular resolution. Although effective, the number of resolutions and the size are constructed and fixed once the model is completed. We apply dilated operation as key components in our network, which can learn features at different spatial and temporal scales under a single stream architecture. The model consists of 4 components: video preprocessing, feature extractor, embedding generator, and similarity calculation. The video preprocessing handles representative steps by partitioning it according to scene change. The feature extractor is a denoising autoencoder, including 2 excitation paths, both with a validation designed for identifying region distant feature among frames. At the end of both tests, a squeeze and excitation module is added to improve the attention capability. After the autoencoder has been well trained, we take out the trained encoder and use it to generate the embedding of the video. We translate it from a high-dimensional space to a low-dimensional one by taking the average among the channel and the temporal axis. Finally, we use the embedding to compare the similarity of the views. This step is based on strictly comparative scene inflows of anchored positive and negative reviews. There are 3 loss functions in our model, including mean square error, to compare the original depth sequence and the recovery of the boundary repeated. Contributor loss combined with boundary cross-contributor loss for the similarity for protection step. There are 2 essential operations in our feature extractor process. First is the design of dilation. The standard convolution has a dilation rate 1. Dilated convolution is then expanded without loss of resolution of the outer layer and without increasing the number of parameters. Our first step explores the spatial dimension by applying parallel convolution with different rates. So we focus on the temporal axis in another tab using step convolution, LCM layers with variations. The above parallel filters are lots of channels. Therefore, we adopt a squeeze and excitation level for applying weight to channel dimension. In a squeeze operation, we offer a global average proving to generate global statistics. In an excitation operation, we learn the importance level of channels by employing fully connected layers with different activations. So back to our overview of proposed architecture. The goal of feature extractor is to retrieve representative features from the video. This figure shows the basic idea of the extractor architecture. It has an encoder and a decoder. The 2 excitation paths emphasize the diversity in spatial and temporal resolution respectively. The rest of the text in the encoder contains a space and excitation block to improve the attention capability of our model. and generate the weighted answer which is able to distinguish and recover videos. The proposed approach is to evaluate on 3 data sets when compared with several methods. In all cases, we use a mean average precision metric to evaluate the quality of video rankings. As can be seen, our model achieves superior performance in several tests and remains quite competitive compared to other works. We also investigate the contribution of different modules in our model. We test the four configurations shown in this figure. BCD-L2 gives a two-path structure, but has only 2 dilation rates in each path. BC gives the whole dilated convolution citation path, but deletes the lower path. CL keeps the whole dilated LCM excitation path, but deletes the upper path. To validate the necessity of multiple resolution, CL keeps the two-path structure, but there is no dilation at all. Our proposed method BCD-L4 performs the test. CL performs the work which validates the importance of using dilation. BCL performs the EL, which indicates the spatial characteristic plays a more important role than temporal characteristic. BCD-L2 replaces BC and DL, which indicates the notable impact of using our two-path excitation structure. In conclusion, we have proposed a denoising auto-encoder program for video retrieval problem that employs horizontally set dilated convolution and dilated LCM layer with the attention mechanism. The model learns a multi-scale spatial temporal representation of a video in a single stream network. We also conduct several experiments to prove our model outperforms the other non-dilated counterparts. Thank you so much for your time and attention.
Yeah, thank you. Okay, our last paper talk and our last video. Okay, do I have it already downloaded? I think I do. Amazing.
Hello, everyone. My name is Han Zhou, and I am delighted to be here today to present our work titled Geometry Enhanced Reference-Based Image Super Resolution. Our focus lies on the challenging task of reference-based super resolution, which distinguishes itself from single image super resolution. This particular problem involves enhancing the resolution of a low-resolution image by utilizing a reference image that shares similar content. Several critical challenges persist in this task. Firstly, establishing a precise correspondence between the low-resolution image and the reference image is essential to ensure accurate feature transfer. Secondly, synthesizing more realistic textures necessitates leveraging the transferred reference features effectively. Some of the recent devices are furnished with multiple cameras with the purpose of augmenting the overall photographic experience. The included cameras possess different focal lengths, enabling users to capture photos and videos with divergent fields of view in unison. The image pairs or triplets obtained via a multi-camera system can be regarded as a specific reference-based super resolution configuration, in which the low resolution and reference images share a portion of the field of view. Traditionally, reference-based super resolution methods have primarily relied on matching local patches to estimate correspondence. However, in the case of image triplets obtained from a multi-camera system, there exists a robust geometric correspondence. Recognizing this characteristic, our research aims to leverage geometric matching to enhance the performance of reference-based super resolution. Our initial investigation focuses on 2 distinct types of feature matching. Firstly, the patch matching method enables the model to identify the most similar patch from the reference image, allowing for flexible matching that covers any region within the low-resolution image. Conversely, geometric matching produces matching results that strictly adhere to a specific geometric transformation, resulting in blank spaces outside the overlapped region. As a consequence, the alignment outcomes of these two methods demonstrate noticeable disparities, as illustrated in the accompanying figure. We additionally present a detailed examination of 64 by 60.
Sorry for this. I'll try something wrong with this video.
Using separate presented geometric matching to enhance the performance of reference-based super resolution. Our initial investigation focuses on 10 distinct types of feature matching. Firstly, the patch matching method enables the model to identify the most similar patch from the reference image, allowing for flexible matching that covers any region within the low-resolution image. Conversely, geometric matching produces matching results that strictly adhere to a specific geometric transformation, resulting in blank spaces outside the overlapped region. As a consequence, the alignment outcomes of these two methods demonstrate noticeable disparities, as illustrated in the accompanying figure. We additionally present a detailed examination of 64 by 64 patches. As depicted in the figure, the leftmost patch represents a reference patch, while the rightmost patch represents a low-resolution patch. The two central images showcase the aligned results obtained through patch matching. Notably, the patches derived from patch matching exhibit noticeable inconsistencies in challenging regions, such as edges and corners, stemming from inevitable mismatching. On the other hand, while geometric matching is unable to handle the regions beyond the overlap, it displays superior smoothness when compared to patch matching. Recognizing the strengths and limitations of these two methods, we straightforwardly explore their combination as a potential avenue for a more effective solution. Presented below is the comprehensive framework of our proposed methods, encompassing two primary components. The first part entails feature matching between an ultra-wide and wide-angle image. Here, the ultra-wide image is utilized as the low-resolution input, while the wide-angle image serves as a reference, sharing approximately 1/4 of its content with the ultra-wide image. This part of the framework involves the utilization of both a patch matcher and a geometric matcher. Moving on to the second part, we tackle the challenge of matching between ultra-wide and telephoto images, where a significant disparity in the field of views exists. To address this issue, we leverage geometric correspondence to train and enhance a patch matcher specifically for matching these two image pairs. This enhanced matcher, aptly named Geo-Enhanced Matcher, facilitates robust matching between the ultra-wide and telephoto images. To achieve matching between the ultra-wide and wide-angle images, our approach involves obtaining two matching maps using separate matchers. Subsequently, we align the features from the wide-angle image based on these matching maps, resulting in two sets of aligned features. To capitalize on the respective advantages of these aligned features and mitigate the risk of introducing blur through direct fusion, we incorporate a deformable convolutional network to further refine the reference features based on these two inputs. The acquired reference features will be combined with low-resolution features and telephoto features to produce the super-resolution outcome. To overcome the difficulty of training an accurate patch matcher between ultra-wide and telephoto images along with the whole framework, we choose to pre-train a patch matcher using the estimated geometric correspondence as pseudo-ground truth. Inspired by D2Net, we use the triplet margin ranking loss to achieve this target, which is trying to minimize the distance between positive pair and maximize the distance between negative pair during the training. We set the feature patches matched by the geometric matching as the positive pair and set the most challenging pairs lying beyond the square local neighborhood of dimension 2K as the negative pair. Finally, we equip a patch matcher with this trained feature encoder, resulting in a matcher that can well establish correspondence between telephoto and ultra-wide images. We employ a two-stage training strategy. In the first stage, we train the model on 4 times downsampled image. Note that in this stage, Only wide-angle image serves as the reference. The loss includes two parts, a reconstruction loss for preserving the contents of the super resolved image, and a reference fidelity loss for forcing the model generating textures close to the wide-angle reference. The total loss is a weighted sum of these two losses. During the second stage, our model undergoes training to adapt to real-world inputs, utilizing both wide-angle and telephoto images as references. Given the absence of ground truth data, we follow the approach of previous studies and adopt a self-supervised learning method. The self-supervised learning process is guided by an equation that incorporates two terms. The first term ensures that the model preserves the content, while the second term focuses on transferring high-resolution details from the telephoto image. For the geometric matcher in our proposed method, we utilize PDCnet that has been pre-trained on Megadeth. To assess the performance of our proposed model, we conduct a comparison between the model trained in the first stage and other models in the fields of single image super resolution and reference-based super resolution. The evaluation results, measured through PSMR and SSIM, establish the superior performance of our proposed model compared to other approaches. We then perform a comparative analysis between the matcher trained with the complete framework and the one trained solely using geometric information. In the figure, we visualize the warped reference images to provide visual evidence. It is readily apparent that a conventional patch matcher struggles to capture the correspondence between image pairs with a significant disparity in field of views. Conversely, when employing the proposed geo-enhanced matcher, more reliable correspondences are predicted, leading to improved feature transfer. We then compare the visual quality of super resolution output. Compared to the previous works, ours can better transferring high-quality textures to the correct portion, especially in the overlap part of the image. By utilizing the geometric matcher and geo-enhanced matcher, ours successfully generate clean textures and reduce the artifact. Thanks for your attention.
Okay, thanks, speaker. Let me now switch the host. 1,
2, 3. I should be here now. Can you hear me?
Yeah. Okay, one moment. So there will be now challenge talks, and one of the teams insisted that their representative should be the person who is connected to Russian Academy of Science. And they also accused me in discrimination and racism. So I would leave now for the protest of this and the challenge talk follow. So, and I switch the host to Edward. Thank you.
Okay, thank you, Dimitro. Can you hear me? Can someone on Zoom confirm that the sound is good?
Yeah, we can hear you.
Okay, perfect. Can you share the slides from the lab? Should I do it myself?
You have the, yeah, you can do it, or I can.
Okay,
you have the
try
share.
to do this. Share screen, slides. Do you see it now?
Yeah, works perfectly.
Okay, perfect. So yeah, quick talk about the challenge. Again, thank our sponsors who allowed us to increase the prize pool by a factor of 5, which is super nice because, you know, it attracts a lot more participation. A quick note that the actual prize winners have not been determined yet because we need to validate the solutions, look at the licenses, etc. So this is, you know, just temporary leaderboards. What is new this year? So 2 big changes. One is that last year we did only stereo after having both stereo and SFM, that is 3D reconstruction from multiple images in the previous editions of the challenge. It was mostly because it was difficult to set up at Kaggle. We actually managed to do this year. So we installed CalMap, we installed Cornea, along with some state-of-the-art local feature methods and matchers so that people can actually get started without having to install a lot of dependencies, which is not trivial. And we also addressed one of the problems from last year, which is that there was a disconnect between the data that participants could see and play with publicly, and the one that was the hidden test set that the evaluation actually runs on, because the way that this works is a code competition. You submit a code in the form of an IPython notebook, a Jupyter notebook, and this runs on a virtual machine offline. You don't have direct access to the data. So we actually solved this problem this year. We have 3 data sets, all new. One is historical preservation data, so it's really cool. It's images like the ones that you see here. They are quite different from what we had before, because they have non-upright images. They have images acquired from land cameras and also from drones, so from high above. And we have extremely high resolution images, which is something that you don't often see on these kind of public benchmarks. A second data set is the urban data set. This is more traditional cities, but it also has very challenging situations, such as very symmetrical structures, repeated patterns, strong viewpoint changes, a lot of day-night changes. And the third data set is the Hyper data set. Hyper is one of the companies that co-sponsors the challenge, and it's more of an object-centric nerve kind of scenario, right? So such as these images that you see in here. There is a short video that I hope plays well. So this app is publicly available. You can download it and use it to build your nerve models. Sorry, and these are some of the examples of the models that you can get, which is quite cool. To participate, well, now the challenge is over, of course, but it's all very simple. You can just go on Kaggle and submit code with a notebook. You can play with the public data before making a submission. So it's all very easy. And these allowed us to increase participation from previous editions, as you saw at the very beginning. We got some stats on what this looks like on the hidden data, and this is what the numbers look like on the heritage data set. You see that there is some variation. This is extreme on the case of hyperdata, because these are smaller object-centric data sets, and typically you either fail completely or you succeed completely. And this is the results on the urban scenes, which are surprisingly less variable than in the other cases. We'll have 6 challenge talks, and I think we can just jump directly into them in the interest of time to give more time to the speakers. The first one is Shengi He, who should be on chat. Kwang, can you?
Yeah, I will transfer the thing. So 1 second. Yeah, I need to reclaim. And then great. The keyboard layout is something that I'm not familiar with. So there you go.
Okay, we are back on time. Only 3 minutes late now, so it's all good.
Okay. Hi, can you hear me?
So yeah, please share your screen and then we'll be on screen.
Okay, let me share my screen. Okay.
Yeah.
Okay, can you see my screen?
Yeah.
Okay, let's begin. Hi, everyone. We present our first place solution in MSC this year, and our team member in this competition includes Xingyi He, Dong Litan, Sida Peng, Jiaming Sun, and Xiaowei Zhou. Here is an overview of our pipeline. In general, we use a 2-stage and a hybrid matching strategy for robust matching. However, directly use these matches for SFM faces problems due to the multi-view inconsistency, which will be analyzed later. And therefore, we devised a cost-to-find framework to solve this problem. In the matching phase, we first construct image pairs by the global descriptor. And then we detect the image rotation by performing a lightweight sparse k-point detection and matching on rotated pairs. The pair with the max number of inliers are used for the next stage matching. Based on the rotated pair and the first stage inliers, we crop the overlap region and resize the image to align the scales. The second stage of matching is performed using both detector-based and detector-free matches. However, problem exists when directly using the previous matches for mapping. Recall that recent detector-free matches such as Lofter A-span former use a coarse-to-fine matching mechanism. This two-view nature leads to a multi-view inconsistency problem. It's hard to construct feature tracks across multiple views, which is crucial in SFM. Therefore, we devised a coarse-to-fine framework to solve the above problems. In the coarse mapping phase, our idea is to scarface match accuracy for consistency by match merge and reconstruct a coarse model. And then we improve the pose and the point cloud accuracy by our iterative refinement pipeline. And in the coarse SFM phase, we first aggregate matches of each image by its matching pairs. And then for each image, we perform NMS over aggregated matches and merge matches to the point with max match confidence within the NMS window. And we reconstruct the coarse model based on the merged matches. Then, given the coarse model, we refine it for higher pose accuracy by our iterative refinement phase. Our idea is to iterate between multi-view matching refinement module to refine feature tracks for higher precision and use geometry refinement to improve pose and point cloud accuracy based on the refined tracks. Okay, let's dive into our feature track refinement module. The input of this module are coarse 2D locations of feature tracks, and the outputs are their refined 2D locations. Features of corresponding image patches are extracted first and transformed by our multi-view feature track transformer. And then tracks are refined by the multi-view feature correlation. Okay, more details will be shown in our research paper. And the results on the computation this year show that our pipeline using detector-free matches and our iterative refinement help us to achieve the first place. And substituting Lofter with DKM can further bring improvement in our framework. We also show running time on the training things, and our refinement phase does not bring too much running time overhead and can gradually improve module accuracy. We also evaluate on other data sets to demonstrate the effectiveness of our pipeline. And a research version of our framework using a single local feature can consistently outperform PixSFM, which uses the same matches. Okay, we further show some applications of our framework on some challenging things. Our framework can benefit downstream tasks such as novel view synthesis and the dense reconstruction of texture pool objects. Okay, thank you. Now I stop sharing the screen.
Yeah, any questions from Zoom or no? If not, for the sake of time, I will move on to the next.
Okay, thank you.
One second, I need to reclaim host. Don't leave, don't close. Okay, good. Always scary. Yeah, and then let's first find that page. Slides, yeah. Challenge, yeah. And oh my gosh. Okay, that should do it. Okay, yeah, 1 second. Let me go back to, no, not that. Sorry. Can you try speaking? Igor? Hello? Let's see.
Yeah, hello. I'm
Yeah,
so
we can
sorry.
hear you.
Yeah, my other team member, Vladislav, would like to start our talk today. So I will join after him.
Okay, so who's the other member? Oh yeah, I found it. Sorry.
Thank you.
Yeah.
Hi, hello everyone. Do you hear me?
Yeah.
Oh, nice.
I'll be the slide monkey.
Yeah, thank you. Hello everyone again. I would like to share our solution from second place. We are here present with Igor. So let me start. Next slide, please.
Yeah, sorry, hide. Yeah, there you go.
Yeah, nice. Yeah, here is our architecture. And to be short, we used superpoint and superglue for component matching and call map for reconstruction. But to be precise, I will go step by step. So first step is to correct orientation of a sequence of images. We apply some convolutional network to do this, and we have corrected orientation of our sequence. Next, we proceed to feature extraction stage and matching. Here we use here we use superpoint and superglue, as I said, with 3 input sizes. So it's kind of like TTA of multiscaling. We can cut them, and we use caching for superpoint and superglue to speed up the process. We also used it in half mode. That is it really increased the speed and decreased running time. I need to mention important things that we didn't use any additional retrieval model at all. And we selected pairs based on the superglue matches criteria. So we selected those pairs that has more than 100 matches. And we selected them for further reconstruction and further work with call map. So basically, that was our addition of removal of retrieval model. And next, we proceed to reconstruction stage. As I said, we used heuristic of superglue 100 matches, but we finally used multi-run reconstruction stage. That means that we used different matches thresholds, and for each matches, we did new reconstruction stage. And then we pass it to geometric verification function of call map that is doing additional matching and geometric verification. And we do it 10 times, and we select the matches that exist in 8 out of 10 cases. That really helped us to decrease randomness of call map. And we also found very suitable to initialize the first image for reconstruction. It also allowed us to reduce randomness as much as we could. After it, we just pass it to the call map mapper, and we have a bunch of reconstructions because we do multi-run, and we can pick the best one among them based on number of reconstructed images, number of points, and so on. Yeah, next slide, please. I need to mention that we tested really lots of matching models. They are all listed here. They were worse in both in score and in time. All of other bullet points I already talked about, but they're just for you to watch afterwards. And yeah, as I said, we speed up superpoint and superglue, and we didn't use retrieval model at all. And I would like to pass the presentation for Igor.
Do I have to ask you on mute again, I guess, maybe? Sorry, not that soon. Oh, not that. Disappeared. And my Zoom controls, I can't find it. Did we exit Zoom by accident? No, that can't be true. Show all windows. Ah, there you go. Magically appeared.
Yeah, I can hear you. Vladislav, thank you. It was very impressive. Let me go to the next slide. Okay, so we iterated many ideas that unfortunately didn't work for us. So we tested test time augmentation multi-crop operation. So with this idea, we came up because some scenes have images of a big resolution. So that's why, to preserve more details for the image matching stage, we applied this operation, but it didn't work out for us. We also iterated with square-sized images with bigger image size. We also thought that it will be reasonable to replace the internal implementation of RANSAC that's inside the call map with our own, but it also didn't work for us. We also used NMS filtering less significant image pairs. Also, because of the big image size, we tried to downscale the scene images. The next thing that we tested, and it was quite promising for us, is the pixel perfect structure from Motion framework. This is a third-party framework developed by some researchers. We tested this framework locally, and we got improvement from 0.71 accuracy to approximately 0.76. But we understood that this framework is pretty heavy on memory, it's computation intensive, and we couldn't run it for all scenes on the Kaggle. And the last two things that we also wanted to test, but we didn't finish, is adaptive image sizes. And the last one is key point matching refinement methods. So one of the promising approaches is given by ADA matcher solution. And the authors of this project, they claim that it can be used by the as a post-processing step after the matches are retrieved from the detectors. The next slide, please. On this slide, you can see what methods allowed us to get improvements. So just very shortly, we started from the baseline that is in the top of the table. We tested manual RANSAC and we got some decrease in our score. But instead, we increased the image size and we got some improvements. We decided to discard the image retrieval task, use exhaustive matching, apply TTA for different image sizes, and also set up an initial image for reconstruction. And you can see the last two things that worked for us greatly. And actually, these things allowed us to take the second place in image matching challenge. This is rotate detection that Vladislav already covered. And also the other thing is multi-run reconstruction. And you can see that the score that we got after using these things is quite good. The next slide, please. Okay. You can find our detailed write-up of our solution on Kaggle using this core code or using this link. This is all from our team. I'd like to appreciate the efforts of organizers and this conference for the invitation. Yeah, we are very pleased Thank you.
All right, I'll move on to then the next speaker, which is, where's
12 video.
12, yes. Which is a video.
This activity, I will explain the solution that achieved the fourth step. Please let me start with my personal background. I am a worker in chemical industry. I am learning new technologies to apply them to solving my research problems. Of course, it's very fun for me to play with Kaggle as a hobby. My wife is always angry with me because I play Kaggle without taking care of my child. This is overview of the pipeline. Each pairs are rated based on their similarity, which is the baseline provided by the host. I said 40 or 50 pairs to be created per one scene. Firstly, superpoint and superglue obtain local feature matches. If the number of matches is smaller than 13 threshold, optimally 30 matches, an image is rotated and processed again. If they cannot find sufficient matches, its pair is thrown away. Otherwise, the matches are adapted and additional matches are obtained using DKN. Finally, the images are divided into 4 sections and key points are assigned, followed by future matching for all combinations using superglue. All of the obtained matches are concatenated together and sent to column reconstruction. The reconstruction process is the same as a baseline provided by the host. I didn't modify that, but I implemented a multiprocessing for the matching and the reconstruction to save the time. In the following slides, I will review the main 3 processes one by one in this order. In the first matching process, the number of matches is counted, it's being rotated. Several images in the given dataset are not sorted, and the matches are not robust again, such as unsorted images. In this example, this region corresponds to this region, but superglue cannot find this. With rotation, it can find matches like this, which are adapted to the pipeline. This slide shows the benefit of splitting a large image into 4 sections. In this case, superglue can obtain about 200 matches from one single image pair. With image splitting, the number increased to almost 3 times larger than the single one. Actually, which does not depend on the original size of the image. Even if the original image is smaller than 2000 pixels, I obtained similar results. In my situation, it outperformed traditional text augmentation. I also found that just increasing the input size of an image cannot achieve this. And I have tried several public matches to combine in conjunction with superglue and found that DKN is the most suitable. This is an example to show the reason. Please watch the steps. These steps was there corresponds to this region, but superglue made a mistake at this region. On the other hand, DKN can detect the correct regions. while TKM is not good at analyzing this approach. So I can say that these matches are complementary to each other. I provided more details in the discussion page on Kaggle. Finally, I'd like to express my gratitude to the competition host, Kaggle staff, and those who provided the public notebooks. Thank you for your attention. And I'm looking forward to seeing you again at the next competition. Thank you.
I believe the speaker is also in Zoom room. So if you have any questions, please do ask the speaker in the Zoom. For the sake of time, we'll move on to the next speaker. Which is here, right? No, that's not. Sorry, here. Yes. Yep.
Hi, my name is Kohei. My talk will focus on the shortlist of image matching. So the shortlist is one of the important things in image matching step. Generally, the shortlist is created using the image retrieval method. I have considered improving this part. As in the baseline code, the shortlist based on the distance of global descriptor is efficient, but their distance function is not reliable. There is no guarantee that images with close distances are well matched in the following image matching step. This scatter plot shows the relationship between image matching and global descriptors distance. A point represents an image pair. The y-axis is the number of key points matched in the image matching step in my solution. The x-axis is the distance of the global descriptors. By looking at this figure, the image matching and the distance of global descriptors seem not to correlate well. To create a better shortlist, I decided to apply a lightweight image matching model to all image pairs. This requires a lightweight matching model be efficient enough. Fortunately, superglue can significantly reduce inference time by decreasing the number of key points. I set the number of key points in the lightweight matching model to 500. So my solution have two types of image matchers. Here is a scatter plot comparing the lightweight matchers and the following image matching step. Clearly, lightweight matchers is more reliable compared to the retrieval-based method. The lightweight matcher allows us to filter out noisy image pairs accurately. By extracting the k-nearest neighbors for each image, I got a compact shortlist. As a result, for the discovery image set, I was able to cut the size of shortlist significantly. It also helps to improve the accuracy described in this table. Most important things in this contest was how to handle this kind of rotated images. The pre-trained superpoint and superglue model doesn't work well with this kind of rotated images. And for solving this issue, I simply apply the lightweight matchers with 4 different rotation angles and choose the best matched result. This rotation angle estimation greatly improves the accuracy. Here is a takeaway slide. I talked about the importance of shortlist. It is helpful to save the overall execution time. Second, superpoint and superglue can significantly reduce inference time by decreasing the number of key points. I used it for a lightweight matcher for creating a shortlist. Finally, estimation of rotation angle is important in many pre-trained matching models. That's all. Thank you for your attention.
Yes. What model embedding technology uses in MATLAB?
So, what model? So you asked me what model for using image retrieval model. Okay, I use the same model or as baseline code. So it is efficient net B7 IS and ImageNet pre-trained model.
Any other questions? No,
thank you.
14. How do I operate? Where was it? Show, yeah. Come on. Okay. Then who's the? Yes.
Hi, can you hear me?
Yes.
Okay, great. So hi everyone, my name is Yingman Chen, and I'm happy to share my 6th place solution and findings today. And I'm actually new to the image matching area, and I want to first express my appreciation to this series of competition. There are a lot of resources available for me to learn these topics in the last months. And so let me get started with my solution. It is a quite straightforward solution, just combining multiple local affine feature detectors and an LLM matcher implemented by Konya. The LAF detector term being used in this document represents a local affine feature detector modified from the KeyNet AffaiNet HARNet, as shown in the bottom left image. And the overall pipeline combines 4 detectors with a similar structure and a LLM matcher to extract the matches. The matches are then combined and passed through the geometric verification before the code map incremental mapper for getting the image poses. Next slide, please. And I think one of the highlights in my solution is that the rotated images are handled by the matcher automatically. And the initial plan for the competition is to just use this KeyNet, AffaiNet, HARNet, and LLM combination for image retrieval, which should narrow down the number of pairs and generate a drop-dead ROI for slower detector-free matches such as LO, FTR, and DKM. And the matches can also be used for ensemble optionally later. And from my observation, KeyNet, AffaiNet, HARNet, and LLM matcher is pretty good at getting the image pairs. The mean matching distance is a clear classifier for whether 2 images are a pair. The value will be close to 0 for a true pair and close to 1 or no matches for a false pair. And it can also handle rotated image automatically, like the left image here. And I also see that it may perform better than using some global descriptor for challenging pairs in this competition. Like the efficient net B7 would get a similar score for these two pairs, while one of them is a false negative pair with a certain threshold. Please go to the next slide. And one issue of the detector and metric combination is that it is too sensitive to small repetitive patterns in the image pair. It may also give false positive pairs. For example, the markers in the war data set. Yeah, but this can be handled by filtering based on the number of matches. Next slide, please. Yeah, I spent some time in testing detector-free matches, but didn't make them work very well. And then I went back to improve the local feature detectors again. And I observed that replacing the key point detector may add matches on different areas in the same image pair. And it's also able to generate some new pairs in the data set, as shown in the two images here. So Harris detector just adds some more key points in the image. And yeah, next slide, please. And then I found that combining more and more matches from multiple LAF detectors can increase the number of matches and may enlarge the coverage area. The overall score was improved by just combining more matches from different detectors. Next slide, please. And then finally, I measured the performance again after the competition. This chart shows the score on a training set, public set, and the private data set with a different combination of models and detectors. And a quick keynet finite hardnet solution with a single model can finish in 2 hours, and it already ranked about 30th place in the competition. And adding more models stabilize the score across different data sets and improve the overall performance, which leads to my final solution with 4 models that can be finished within the 9-hour fixed runtime. Yeah, so that's all about my straightforward solution, and thank you for listening.
Any questions? If not, we'll move to the last speaker.
We are Felix, and Steve, Philip, and me, Alex, 4 master's students and 1 PhD from ETHC. We would like to express our gratitude to the organizers for this awesome challenge and extend our congratulations to all the other teams for their hard work and impressive solutions. Our goal was to develop a price-eligible solution and could drive the performance of superfund and superfund. Our pipeline begins by predicting and correcting the limitations of the images. We then employ NetBillet to generate a short list of image pairs using the top 30 candidates. A significant performance boost comes from utilizing an ensemble of disk and likeness. In order to match disk and light, we leverage lightweight and highly accurate method developed in ETHC. Additionally, we employ PixelSFM for feature metric key point and final adjustment. And in certain scenes, we enforce shared camera intrinsics within content. Finally, by incorporating hierarchical localization, we obtain absolute totals for unregistered images. Our ensemble achieved a solid 8th place with a private score of 52.3%, representing a substantial improvement over this performance. In replacing a like with superpoint, we achieved a remarkable score of 89% on the set, matching the score of second place on the private leaderboard. Additionally, substituting light blue with super glue reduced our train performance to 87%, and the slower matching speed caused Ensemble to time out on the leaderboard. Light blue is a highly efficient and accurate matcher developed at ETH. Its architecture incorporates self and cross-attention, enabling it to predict robust matches. With early pruning and confidence classification, light blue efficiently discards unmatchable points and terminates early, avoiding unnecessary complications. Light blue, as well as the training code, will be released under a permissive FIT license. Light blue outperforms super blue when paired with super point in terms of accuracy and speed. It improves the score on the trained, public, and private datasets while requiring almost half the time. Recognizing that inflations pose a significant challenge for current feature extractors and matchers, we employed an image orientation predictive model based on a Ruby transformer architecture. After correcting the images, we perform retrieval, feature extraction, and matching, and finally backward the key points of the original image before running processing. Although we noticed a significant boost for Cypress in the scoring, this approach did not yield any favorable results upon submission, leading to a decrease of 4.2% in our public scores. Consequently, all reported leaderboard scores do not use any rotation correction. After obtaining the image pairs from NetBLAT, we extract and match the key points separately for each configuration, and finally concatenate the matches before running pixels event. The most promising pairing was achieved by disk of light blue, resulting in a respectable 43.7% on the private leaderboard. Adding a liked as well as SIF to the nearest neighbor match in the rated place increased the results to our final technical score. Our final ensemble demonstrated promising results, matching the superpoint ensemble with most trained scenes. Both versions of the ensemble achieved near perfect score on the Cypress and Fountain scenes. However, Superpoint outperformed our ensemble by significant margins in the ball, chess, and urban scenes. Despite this, we chose not to use Superpoint due to its restricted license. Once the ensemble was established, we utilized PixelSFM in its low memory configuration for feature metric key point endpoint adjustment. Due to the rotation sensitivity of STGNet features, we decided not to use PixelSFM in scenes where rotated images were detected. Additionally, force and convex use shared and primitives in scenes where all images have the same shape proved to be highly valuable. Incorporating PixelSFM and shared cameras resulted in an increase of nearly 3% in our score. We encountered some unregistered images that had a high number of matches with registered ones. Leveraging log for localizing these remaining images proved to be effective, resulting in a perfect score on the Cypress team and contributing to an overall score improvement of approximately 1.5%. By integrating all components, our solution achieved highly accurate abstraction and counterpose, given the sparse number of views. The ground truth is shown on the left, while our construction is displayed on the right. In conclusion, I would like to express my gratitude once again towards my teammates and the organizers for this remarkable challenge. More information about Light Blue will be released in the upcoming days, so stay tuned. Thank you.
Yeah, speaker for this video is also online on Zoom, so please ask any questions if you have. And let me turn to the final slides, and then I'll hand it off to Luca.
Okay, so thanks to everyone for participating to this workshop and who have participated to the challenge. And I have to apologize for some problems we had, but we will load online all these slides. So I will let you with some questions So if the workshop is serving this purpose, we can discuss later. If we are really near the problem, the real problems, and then does it make sense have hidden test data without a lot of public data also? We can discuss later. Is Kaggle sufficient powerful for structure for motion? We can think to move to other platforms also in future. And if the data is too heterogeneous. And finally, the data set are enough to speak about the large data set? Probably no. So we have to change something. We will see. So I would like to thanks again. Let's discuss later if you want. If you have a suggestion, you can also write out. Thanks.
Thanks all for coming. And again, sorry for the folks in Zoom, sorry for the poor audio quality. It's weird. We had it working and it's not working. I guess that's technology 2023. We'll just ask ChatGPT to solve it for us later. All right. See you all perhaps in the next edition. And again, I thanks a lot for the challenge participants because I think the challenge did make our workshop a huge success in that respect. And it's all thanks to the participants. And again, I just want to give a shout out to Edward, who couldn't be here in person, but he is really the driving force behind our workshop. And also Dimitro, who basically was the person setting up a lot of things, and Kaggle as well. Yeah, I'm a little bit embarrassed that I'm giving this last closing statement, given that I was sort of the backseat person providing students. So thanks a lot again for coming, and see you maybe in the next edition. Thank you. Bye. Yeah, let's close up the Zoom room, and then I think we're probably gonna get kicked out soon. So yeah, stop sharing.